PEPM 2026. I'm Yukiyoshi.
I'm Ning from the University of Toronto.
So thank you for coming, and so please enjoy this workshop. I'm really excited to have all these kind of talks here. Oh, people are coming. Should we wait another few minutes? Since going through the registration security check took time, so I think, yeah, please come. Oh, hi. Please take a seat. So many people. So just wait for another few minutes. Yeah. Thank you for coming. Yeah. So exciting program and exciting audience. So please enjoy this workshop.
Just a few quick notes. So we have our keynote in the first afternoon session. So please remember to come back after the lunch. And if you have any questions after the talk, there's a mic that the volunteer will help pass around. Just raise your hand for the questions. Okay. Maybe let's get started with the first session.
Yeah. So let's start the first session. So please, yeah, I'll be session chair of the first morning session. And the first speaker, oh, people are coming. Yeah, please join. Come. Yes. The first talk is whole refinement for type and example-driven synthesis, and the talk is given by Nick. So, yeah.
Yes. All right. Hello, everyone. Yeah, thank you for introducing me. I'm Nick Mulleners from Utrecht University, and I'll be presenting whole refinements for type and example-driven synthesis. This joint work with my supervisors, Johan Jering and Wouter Svierstra. What do we mean by whole refinements? Well, you can imagine a programmer starting to write a simple program, and they might start with a type signature and some assertions or input-output examples. And then we have a start of a program. You see this circle with the 1 in it, we call it a whole. This is the starting point of the program which you will continue from. And it would be nice if the compiler could help you along when writing a program, because you've given all this information about what you want the program to do, so why does the compiler not tell you what to do, right? And this often happens. For example, in Haskell, you get these suggestions based on the type of your whole. So it infers that the whole has a certain type, and then you get a bunch of suggestions. And this is really nice, except that in this case, the function skip that we want to define should just remove the first element of a list. And most of these functions really don't do that. So how can we find the ones that actually match the input-output examples? So with a bit of work and some equational reasoning, we can go through all of these suggestions and remove most of them. So first, for example, reverse is a full implementation already. Like, it doesn't introduce any new wholes. So if we would suggest reverse, it would just evaluate to the wrong output, because it reverses the list and it doesn't remove the first element. That's very easy, but then a bit more complicated is with map that introduces a whole. You can already evaluate partially the skip function implemented as map, and then you get a list with holes in it, but we can already see that the list has 3 elements because map retains the list length, and the expected output should have length 2. So again, we can discard this suggestion. Now it gets a bit more interesting. So the const function just ignores the second argument. So we ignore the input of the skip function. And if we use some equational reasoning, we see that now skip 1 to 3 should be equal to just this whole that we've introduced. But we also know that this should be equal to the list containing 2 and 3. So now we get this constraint at the bottom. The whole 2 should have type list of A, and it should be equal to the list 2, 3. But this is not possible because we cannot just come up magically with a value of type A. So we cannot just introduce these 2 and 3. So we call these magic outputs. And we can use this to say that the constraint on whole 2 is not feasible. And therefore, we can discard this suggestion. OK? Filter is a bit similar. Here we have to do a little bit of reasoning. We can say that in order for the filter apply to the list 1 to 3 to return the list 2, 3, 1 should be mapped to false and 2 and 3 should be mapped to true. Right? But once again, this whole has a polymorphic type, and so we cannot just create any values of type A, but we can also not inspect the values of type A. So we cannot distinguish between the values 1, 2, and 3, and thus the output cannot be different for different inputs. So again, we can say this is infeasible, and filter is not a valid suggestion. Now, for fold R, it's a bit more complicated because we're dealing with recursion. First, I'm going to look at the 2 input-output examples that we started with. And the second one, we're going to rewrite. Because since the values of the monomorphic instantiations, like these 4 and 5, they might as well be any other values, right? Because we cannot inspect them, we cannot produce them. All we know is that skip takes the like a 4 and a 5 and returns a 5, but this 5 must have been passed around from the first list to the second. And similarly, we can deduce that then skip applied to 2, 3 should return the singleton list 3. Right? And now we'll do some equational reasoning again. First, we introduced the fold R, and then we evaluate fold R once. We inline it. And then we know that fold R applied to the list 2, 3 is equal to skip applied to 2, 3, as that is the refinement that we're currently looking at. And then we can use the input-output example that we found, that skip 2, 3 should be equal to the singleton list 3. And then we get the following constraint at the bottom. And once again, we can see that there is a magic output here, because this 2 cannot come from anywhere. So essentially what happened is that the skip function returns, it drops the first element of a list. And to define something in terms of fold R, we have to define it in terms of the recursive call on the tail of that list. So that we throw away the second element of the list, which we actually need to compute the skip function. I hope that's clear. OK, so all of the suggestions so far can be discarded. And then we come to pattern matching. And we can actually always pattern match. We cannot find a contradiction in a pattern match as long as the variable that we're pattern matching on is actually an algebraic data type, right? And so what we can see is that now we have found one valid suggestion, and following that, we can compute the next suggestions, and these actually give the implementation of the skip function. Now, this is not the most interesting function, so you're probably not super impressed. But of course, we can do a bit more later. But first, let's look at this general pattern, right? We use equational reasoning to isolate the constraints that are on the holes. And then we compute the feasibility of these holes by taking parametricity into account. So that's where we really want to see how the types interact with the input-output examples. And this brings us to the first part of my work, the taxi reasoner. It's a type and example-based inferencer. And then what it pretty much does is it computes a normal form for input-output examples that are also constrained by a polymorphic type. So this input-output example that we saw before, we can say, like, it doesn't just constrain the input list 1, 2, 3, but it actually constrains any input list that has 3 elements. And here is a formula for this that exactly describes the input outputs that are constrained by this pair of input output and polymorphic type, right? So to see a bit how that works, like we can, for example, also have ambiguity in the input. When the input list contains 2 ones, then we say, well, for all x and y, there exists a z, which is either x or y, such that skip x, y returns the singleton list z. And we can use this to also find conflicts in a pair of input-output examples and a polymorphic type. So here we can see increment function, which is defined for some polymorphic type A, which is not really possible because we cannot just increment any value. And so we see that this magic output that we saw before, the 3 in the output list, is represented by this empty constraint, like Z should be in the empty set. Right? And the dotted line around this result shows that it's incorrect, infeasible. What we can also do is to find a bit more complicated conflicts. So once again, we have a function with a too general type, because max should have some ORD constraint to compare the elements. And if we compute polymorphic example constraints, we get that max x, y should both return y and x. And I hope it's clear that that will, it's easy to find a contradiction here. Right. What we can also do is a form of program extraction, because like I said, like we can generalize these input-output examples to some normal form, but in the end what we're looking for is the perfect generalization in a sense of these input-output examples, namely a function implementing them. But we can find a partial function implementing them by just taking those polymorphic constraints and turning them into a simple pattern match. And then at the end, we just say, well, we don't know what to return for any other output. But at least this shows that we can find a partial implementation that satisfies all the input-output examples, and thus the input-outputs are not contradicting each other. Right? But this also will become useful later. Yeah, one more thing that I wanted to talk about, like we saw max without the ORD constraint, so how can we deal with the ORD constraint? So what we essentially do is we introduce another function, max prime, that replaces the ORD constraint with an ordering argument, which is either less than, equal to, or greater than. And then the compare function, which uses up the ORD constraint and turns it into an ordering, basically. We can get a max prime, which is a fully polymorphic function, so not ad hoc polymorphic anymore. And then Taxi can reason about this and see that these constraints are actually not contradictory. And in practice, we don't have to do all this stuff. We can just, this just happens automatically, and we get some sort of if constraints within our polymorphic example constraints. Right? So now we can reason about a lot of different pairs of input-output examples and polymorphic types, or ad hoc polymorphic types. And now we want to do something more, right? Like we already saw a hint of this before, like if we have this skip function and we know that this is a valid refinement and we have some new suggestions, we pretty much wrote the function for the programmer, right? And we can go a bit further and actually do this, like we just pick the suggestions for the programmer, essentially. And this turns it into a program synthesizer. So here's the function nub, which removes all the duplicates from a list. So it needs some equality constraint, and then we have a bunch of assertions on how it should behave. It's not so important what exactly those are, but what driver does, which is the synthesizer that we've defined, is it just generates a bunch of refinements that get the right program. And the interesting part here is that every refinement that it finds, so every whole refinement that we see here, is actually the first valid refinement the driver tries. All the other one that it tries, it can immediately discard. So this is actually just not only a correct program, but it's the very first program that we find. Now, how does that work? For example, for the first hole, we have a list of possible refinements, and first we try to just return the variable axis, or introduce nil, or cons, a map, or filter, and those all don't work, but then fold R is the first one that actually works. And then below that we have pattern matching, which is never tried because we saw already that fold R works. And we can go through the whole list of refinements. So for the next hole, we have a slightly different context, so we have slightly different refinements. But again, the first two fail, and then cons is the first one that matches, and it's actually what we want. Again, for the next case, bit easier. For hole 4, we just find that the variable x has the right input-output behavior. And then again, we try a bunch of different refinements, and this time we see that filter already works, so we don't have to try fold R. And finally, the most interesting part is where example coverage checking kicks in. As we saw before, we were able to extract a partial program, but this is in terms of pattern matching, and we can check if all the cases are covered. And in this case, the program that is being extracted is actually a total program. And this is very easy to check, so we know that we are done with synthesis. So what we can see here on the left is like, it's maybe a bit funny to read, but we have some x and y that are in scope, and if x is equal to 1 and y is equal to 2, then we expect the whole to be true. And if x is 1 and y is 1, then we expect it to be false. And as such, the polymorphic example constraint covers all possible combinations of x and y that we can observe. Okay. And then in the end, we get this result, and driver returns this implementation, which is valid, but it is a bit cheating in a way, because we had all these refinements, and it was very convenient that always the first one that matches was actually the one that we are interested in. So the question then arises, like, who decides which refinements we can have, who decides in which order they are tried? And well, we can leave it up to the synthesizer to pick something nice, but we can also decide ourselves. And that's why driver is based on a tactic language. And these tactics are very simple. They pretty much just usually introduce a function. So, for example, we have the intro map, intro filter, intro fold, etc. that just introduce this function and apply it to a variable in scope and do all the necessary work, like ATA expanding, holes, and all that stuff, in generating new, fresh variable names. And then we can compose them. We say, like, the eliminate tactic just tries one of those eliminators, and then the step tactic tries to introduce a variable or a constructor or eliminate, and then the synthesis tactic just repeats this step and just repeatedly fills holes with the same tactic. But you can imagine that there's many different tactics that would apply, and in a way this creates like a interactive synthesizer. Now, it's not very clear here yet which refinements get tried first, right? We just say this one, or that one, etc. And we want a bit more control there. So we have a biased choice constructor. So for example, the variable, once we introduce a variable, if it works, right? We don't have to try anything else, because it doesn't introduce any new holes. So actually, any refinement that doesn't introduce holes, we can use this biased choice operator to just ignore all other refinements that we would try. But the interesting ones are the ones where we do introduce holes. But we can do what we call branch control, which is where if we try map, and we know that map is a valid refinement, then we also know that fold is a valid refinement, because we can re-implement map using fold. So if map succeeded, then why would we try fold? It would only re-implement map. And kind of the same for pattern matching. Filter is different, but if map succeeds, then we know that filter will not succeed. So we also don't have to try it. There is, of course, the case where both map and filter would succeed, but then you just have the identity on lists, and that would already have been caught by the intro var refinement. Okay, but then still, we don't know, like, do we introduce a constructor first or an eliminator? And for that, we have a weighted search. So in fact, all these refinements have a weight assigned to them. We can choose whatever we want, but typically it's we don't want to introduce too many eliminators, so we give them slightly higher weight than, for example, constructors. Okay, and yeah, all this together brings us to some benchmark. We have a synthesizer, and we want to try to see, like, how well does it perform. But essentially, it's very hard to compare this directly to existing synthesizers because they usually don't really focus on this specific form of synthesis where the user is involved with tactics. So we just try to see how these different techniques that we implemented, how they improve the synthesis. So we have a basic synthesizer that just uses like input-output examples to check if to discard incorrect programs, and it's based on the types. But the feasibility specifically here is about like introducing this parametricity constraint, because this is what we do that previous synthesizers have not really done. And we see a very slight improvement of like 10% when we use this feasibility. And there's one example where it's like 3.6 times as fast, but it's not very impressive. And the reason is that it just doesn't occur very often that the parametricity really plays a big role in the synthesis. However, when we have this feasibility, this unlocks other kinds of analyses like the coverage checking that we saw and the branching control. And these individually also have some speed ups, and even combined they can have a speed of almost 5 times. And in some cases, much more. And what you really see in the benchmarks is that there's just specific cases where, for example, coverage checking works really well. And this is particularly the case when we have ORT and equality constraints, because a lot of small decisions that might have to be made at the later stage of synthesis can just be shortcut, and we can just find a correct solution immediately. And branching control works particularly well for functions that would actually use something like filter or map in addition to fold R. And this is because what branching control really does is if we can define all those functions in terms of fold R, but filter and map are more efficient, and we will more likely find a solution faster. But we can actually add those to the synthesis procedure without any overhead, because we only have to check one of them every time, right? So the cases where we actually use filter and map, this leads to a big speed up, and in other cases it might have some benefit, right? Right, that brings us to the overview. So we have some types and examples and tactics, and those all are passed to the driver, and driver interacts with taxi to make sure that all the intermediate programs are correct, or at least don't contradict the types and examples. And this returns a program tree with some weights on it in which we can search for programs. Yeah, and that's pretty much it. Do you have any questions?
We have 10 minutes or so. So, any questions? Yes.
I have 3 questions. Choose any which one.
Yeah.
I have 3 questions. Choose any which one. Thank you for the talk.
Yeah.
First one is, could you eliminate the parametricity you have here, that you exploit here by unit types without equality? So a number of different unit types, which would capture part of the parametricity you're exploiting here. And the second question is like, why are you using filter, map, and then fold R, and then case, since the latter case would consume all of them if you at least has function, if you also have function composition in there as a pattern for inferring. And the third question is, have you compared this to let's say Claude Code and see what that one gives you? Thank you.
Let's see, I'm not sure if I understand your first question exactly. Is that
so instead of having for all alpha, list alpha to list alpha, you have just list of a particular unit type. You need multiple ones for every type variable. You need one, just a unit type without equality, and going to list of unit type, right? And then the examples would actually also be just 1, 2, 3 would be mapped to unit element.
I think this sounds a bit like there's this paper on parametricity where like property-based testing is made easier by using specific types instantiations, right? In some cases you could do that, right? You could have like a simpler type, but the whole point is that we want the user to provide monomorphic input-output examples that use integers, for example, and then see how those match, how the inputs actually are passed to the output. So if you would turn it into units, then you would sort of lose this connection, I would think, but maybe I'm missing a bit the point. We could talk about it later. The other question I remember, let's see, yeah, you said, why would this case be here? That's it.
Why would you have the first three cases?
Yeah, why would you have the three?
Why not just go straight to intro case?
Yeah, because it's not the most efficient way to a correct program, right? So we know that if it can be implemented with a map, and we try to implement it with a map, it's much faster. And pattern matching always would work, but it tends to lead to overfitting, especially because we start with few input-output examples. You could just start pattern matching, and in the end, there's no examples anymore, and that's it. So the whole point is that we saw this program extraction where we turn the input-output example into a program, and this essentially does a bunch of pattern matching. But the interesting part is generalizing beyond the examples in a natural way, and that's where these combinators are for.
And did you try Claude Code or anything like that?
Right, yeah, they definitely outperform what we do. Yeah, the only thing that makes it interesting to me is that we have guarantees of correctness, right? We can show that these refinements actually make sense and lead to a solution. And if we have a bunch of refinements, we can say like, these are the refinements that would work and these are the refinements that would not work. Whereas Claude just generates stuff. And yeah, you can test that those are actually what you want. But let's say you have a program that's very complex and we just want one small next step for the user to pick from, because these synthesizers generate just a bunch of things and you can look through them and find the one that you want. But sometimes it's nice to just know this one step brings me closer to something. And then maybe Claude could pick up again and give a correct implementation. Yeah.
Yeah. Any other questions? Yeah. Yes.
So when you're generating the examples with the ordering and equality, do you have to, how does that work? Like, how do you know which equalities and inequalities matter and which ones don't?
So let's see. This part, you mean, right? Well, we pretty much say all of them are relevant. In this case, we only have 2 inputs, so we just say we use the compare function and add it to it. What we do, this is not what we actually do. What we actually do is just take all the inputs and create like how do you say that? A set of equivalence classes. And in the case of ORD constraint, these are ordered equivalence classes, and equality constraints, it's just equivalence classes. And then we use that as an additional input to this helper function. Yeah.
So does that mean it works? Does that mean that this is only working specifically on EQ and ORD and not on any arbitrary type class?
Yes, exactly. Yeah. You can imagine, for example, monoid, if you would have this is something that I didn't really go into that much, but we need our types to be strictly positive for this to work. Because if you have an input argument from like A to A, then you can apply it many times and you wouldn't really know whether it would eventually lead to the output that we want or not. And so many, these constraints can usually just be replaced by the functions in the dictionary that they represent. And for ORD and equality, we can turn them into something that's strictly positive. And for other constraints, that's harder or impossible. Yeah.
Are you saying that you can handle arbitrary or strictly positive ones?
Sorry?
So his question is about whether you can handle only ORD or EQ or not. But your answer seems to say that arbitrary, strictly positive ones are okay.
Yes, yes. But most constraints do other stuff that's more complicated than that are not strictly positive anymore. Or like even if the function that the constraint implements is strictly positive itself, once you put it into this function signature, the whole thing is not strictly positive anymore. So yeah, that's essentially.
Okay, thank you.
Yeah.
Yes, yes. Please wait for asking question because this is being recorded.
Does this work with higher order functions, synthesizing higher order functions? It kind of looks like it should. And if it does, why replace with compare x, y, and not just compare? So if I wanted to synthesize, if I wanted to pass in a function here and use that in my synthesis, does that work?
As a part of the function that you're synthesizing, you
Yes.
want a higher order
Yes.
function? Yeah. No, that does not work.
Okay, is there a fundamental reason, or does it just not work in your implementation?
So if you have the thing is just that you can synthesize programs like that. You just cannot get any additional reasoning like that. So you didn't really explore it. Because if you have a function in scope that just turns an A into an A, and it could be anything, then you cannot do any of this reasoning where you show that an output cannot come from the input, because there could be an arbitrary amount of applications of this function that you're passing. So there, you could have it as long as the function that you're passing returns, for example, a Boolean or an ordering or something like that, something finite. But if it's something like A to A, that doesn't work.
I see. Thanks.
We have 2 or 3 minutes. If I can ask some silly question, what is the most complicated example you have succeeded? Well,
Oh yeah, not super spectacular, but let's see, something like sorting, like it can implement.
You mean what kind
like
of sorting?
List sort and yeah. I think that's probably the most complicated. Yeah.
Okay, thank you.
So yeah, it's not groundbreaking, but it's more about these small refinement steps that lead you to this
Yeah,
solution.
so
Yeah.
we can gradually develop our programs using your tool. So it's implemented and we can use it.
Yes, but then again, it's a very specific setting with very specific types, specific ways in which you can define your input-output examples and specific refinements that are possible. So I don't know of any languages currently that it would perfectly fit into. Maybe like the Hazel programming language would be a nice way to introduce these things, because they have already some of these things implemented. I know that polymorphism was added recently. So this would be a nice place to actually use it in practice. But yeah, you can use the system and synthesize programs with it.
I'm sorry to ask too many questions, but if I am a user of your system, maybe writing the tactics would be very difficult for me. Well, maybe.
Possibly, yeah. So that's why there are like existing tactics that you can use and just explore the programs that it generates. But yeah, writing the tactics would be a bit more complicated. And it would be nice to have some interface there to make this easier. Yeah.
Okay, thank you very much. Thanks again.
Thank you.
Next speaker. Yep. So the next talk is about inferring typing rules for contextual sugars, and the talk is given by Tai-Lai Yu. Yeah. Yes.
So, bonjour everybody. I am Tai-Lai Yu from Peking University, China, and the topic of my talk is inferring typing rules for contextual sugars. So, talking about sugars, I mean syntactic sugars. They are language construct derived from other constructs. The textbook example would be the let binding, which desugars, yes, the term is to desugar it to an application of a lambda abstraction. And here I would use a fancy D to denote desugaring, and from the notation it recurs down the subterm. So if there are more sugars in E1 or E2, they are also desugared. And it is, well, used everywhere. So sugars enable reuse of existing constructs. For example, in real languages, they use sugars to keep a small core language and provide sugars as a friendly interface in the surface language. So there are a bunch of examples: dual notation, list comprehension, async await. Even in C, like the pointer to member access is considered a sugar. And we can also, some languages also allow users to define custom syntax as macros, and we can broadly think of them as user-defined sugars because they are also things that derive from other constructs. So I said it enables reuse because, for example, you don't need to evaluate the sugar. You only evaluate what it desugars to. But consider what this works in reality. So for example, in type checking. So real languages, they often manually type check the syntactic sugars before desugaring. This is against the reuse I just said. For example, in GHC Wiki, the Haskell compiler, it says they do this, although this complicates the type checker because like there is a chance that your desugaring and type checking has a mismatch, but it improves error messages. So what does this mean? If we just want the reuse, we can type check after desugaring, but this is quite problematic because the errors are reporting in the desugar code. Think of macros when you used the macros last time and errors pop up in something you didn't write. You have to study the internals of the sugar. So we say this is an abstraction leakage. So the abstraction boundary of the syntactic sugar as a syntactic abstraction is broken. So either solution has problem. So can we get the best of both? So we can directly type check the sugars, but without the additional effort that we have to manually write their type checking. And Pombril and Krishnamurthy came up with a solution. So they, from the core language typing rules and the desugaring rule, they can infer the typing rule of a sugar. For example, this is the let example we just showed. And so the relevant core language typing rules are that of abstraction and application. And the inferred typing rule for let is quite decent, what you would expect. So it type checks E1 first, and then with the binding of X, type checks E2. So the key properties of their inferred rules include abstraction and let's say preservation of abstraction, but they use abstraction for short. It means that no desugared code appear in the inferred rule. So everything is what you have written. No lambda or application show up in that rule. And correctness, which means typing with the inferred rule behaves just the same as typing after desugaring. So there is no point of errors. So how do they do this? We can see that every instance of let desugars to a code of this form. So when we type check this, the typing derivation always starts with a typing rule of application followed by a typing rule of abstraction. And then now the premises are on E1 and E2 desugared, and we cannot go any further. But if we collect the open premises and rewrite them in a form of the surface language, so E1 desugared becomes E1 before they are desugared. So there is a one-to-one correspondence between the collected judgments and the inferred rule. And we can see that inferred rule is just an abbreviation of this partial typing derivation, which is general enough to capture all instances of typing derivations of desugared lets. And this is how they do it. And there are also similar works trying to infer not only typing, but also scoping or big or small big step operational semantics from the disagreeing rules, quite like how they did before. So, but there is a very large limitation. So it is that the supported form of sugars is quite limited. They only support simple pattern-based sugars, and the desugaring process is totally fixed. So from a let, they always desugar to a lambda applied, and there is no any kind of dynamic thing, and no any kind of calculation. So this actually limits their applicability. So can we go a little step further? Can we make things a little bit less fixed? So how to make things less fixed? Then a sugar must be able to, for example, read some context. They must interact with something, the context it is in. It may have remote interactions with other sugars or constructs. And this is what we try to do. So concretely, we identify two purposes that context may be important to express a larger set of sugars. And we call these context-sensitive sugars contextual sugars, which appear in the title. So first, there can be multiple constructs that cooperate remotely. The running example would be a pipe operator in the hack language and also proposed to JavaScript. It is not a functional programming pipe. It's like, for example, on the first line, the pipe is denoted by a triangle on the right. And if we pipe a string ABC to the right-hand side, which is, so the percent sign denotes a hole. So whatever on the left is piped goes into the hole. So it becomes, so the first line would mean that we pipe ABC to concatenate itself with itself. And what we get will be like this. We bind a ABC to a fresh variable x, and then it will be, every hole would become a reference to the x. And the important thing is that the holes, the percent signs, can nest arbitrarily deeply on the right-hand side. For example, within parentheses, within arithmetic operators, it can nest very deep. It doesn't have to be very close to the nearest pipe. So the second line looks like this. So the point is that if we want to write this as sugars, we see that the whole cannot desugar by itself. It doesn't know where the nearest pipe is, doesn't know what variable it binds. So here we introduce a desugaring context, which is the delta here I didn't explain. So delta for desugaring context, very reasonable. So we use the desugaring context to pass down the nearest variable reference to the x that was bound by the nearest pipe. And so when we desugar a hole, we just take the delta out. When we desugar a pipe, the left-hand side is still desugared regarding the outside delta, but we pass down the x reference down so that the inner holes can read it. And a second reason that context can be important is that the desugared code can be of very complex structure. For example, they can be scattered. This is a famous type-safe printf example. So printf of a format string is desugared into a curried function taking many arguments that it wants to format. And the point is that, for example, the person S, which should take a string, it first takes a string and then contributes to a part of the final string to print out, or actually concatenated, and they are separated. So we can do this with the context-free pattern-based sugars as before. I won't go into the details of this example, but the idea is that we can use a desugaring context to accumulate the final string. So the person S, we will see it as a sugar, and then it first takes a string, desugars the left part that takes an argument, and appends the string to the accumulator. Okay, so our work does this. So we introduces context to syntactical sugars, and we provide an algorithm to infer typing rules for a class of them. And the outcome of our inferred rules share similar properties as POPL' and Krishnamurthy, so it still preserves abstraction. And regarding correctness, we say it's sound. We will see why it's incomplete, but it's actually something desirable. And it's sound with respect to type checking after desugaring. But there's also some twists regarding hygiene. We will briefly talk later. So as an aside, our formulation of context is a bit similar to syntax parameters in schemes in Racket macros, for those who know. And they are also an addition to pattern-based macros that can allow you to introduce contexts. So you can also think of our work as typing syntax parameters. So how do we do it? First, we start just like the original work. These are the pipe and hose desugaring rules. We form partial derivations for both of the right-hand sides. And it starts out well for the pipe, but it cannot do anything at all for the whole because we know nothing about what delta is. It has no known structure. We cannot apply any kind of rule. So we actually want the pipe to help the typing of the whole by passing down something relevant to the delta. So here's the first step. So we can think of this inferring typing rules as a fusion. So we fuse together the desugaring rule and the core language typing rule. When a piece of core code is desugared out, it is type checked, and so we fuse them. And then it will be very natural to have the fused form to have context from both of them. So both gamma and the desugaring context delta will appear in the surface language's typing rule. This is very natural because the language will have remote interactions. So then with this partial derivation of the pipe, we can try to rewrite the premises and the conclusion in the new form. And mostly it is natural because like E1 is desugared under delta, and in the rewritten form, it will have delta as it's a part of its typing context. And then E2 is desugared under X, so it is X there. And these still have a one-to-one correspondence. But there are two problems with this partial solution. The first is that we still cannot type check the whole because it actually wants the type of the delta, not delta itself. It still doesn't know how to type check it. And also, there is still a leakage of abstraction. So look at these two x's. You did not write these x's. The x on the left is fine because we can do because the type checking of E2 does not rely on the X binding. It is fresh. So with some clever post-processing, we can remove X of tau1. But this X is the X on the right. It is a variable reference to pass down. So you cannot just erase it. So it stays. And moreover, in more complex contextual sugars, you can think of the desugaring rule passing down a long piece of code as a desugaring context, so it stays. This is not what we want. So we said that we want pipe to help whole to desugar, to type check, but we don't need to pass down everything. We just needed to pass down the relevant information, and during type checking, the information would be the type of X or the type of delta. So we changed the form of the surface language typing rule a bit. Instead of passing the desugaring context itself, we pass down its type. We write as delta tau. And then if we try to write the partial derivation for pipe in the new form, the ones that use delta would just naturally become delta tau. But what about the type of X? So here is the title of where the title of the second step comes in. So we call it early typing because usually you would think that it would be type checked when the hole appears. Now we type check it early, so the pipe takes the duty, and we see that the X is also a piece of the sugar code, so we don't want them. So we can just do the same thing as for the main template, the whole right-hand side. We can also form a partial derivation for X, and so it's a reference. So it starts with a rule for variables, and luckily we don't get any new premises. But anyway, if it has open premises, we would want to put it inside the final rule for the pipe. So basically, the final rule this partial derivation says that the type of X will be tau1. So we pass down tau1, which is the type of the E1 that is piping inside. So this would mostly be the final inferred typing rule for pipe, and we can also, for example, process away the X binding I just said. And for the whole, it would be much easier because it wants the type of delta, and we are passing down the type of delta. So the typing rule of whole would look like this. It just reads delta tau from the context. This is what the nearest pipe passes down. So finally, our inferred rules for pipe and whole would look like this. This will be very much expected. So like everywhere in the code, you get a type of the nearest thing piped down. And as a recap, we have two steps. First, context fusion, and then in context fusion, we introduced the sugaring context as a typing context, part of the typing context of the surface language. And the second step is early typing, which removes the needs of passing down the desugar code in the desugaring context themselves. We type check them early. So we type check, we form partial typing derivations for every template, not just the main template. And this can be a little bit more general. So delta can be not only one piece of code. It can be, for example, a list of terms. Then we would have a list version of them, type version of them. So delta tau would become like a list of their types. So so far so good. So we did so much to preserve abstraction. So what about correctness? There are some technical things about this, so I will go over this briefly. So we did early typing. So there is actually a mismatch in what context to use. We said this X can be type checked under this blue context, which includes the X binding. So why gamma and X of tau1? Why not just gamma? Because this X is written here under the let binding. This has a this is like some kind of local reasoning. So in early typing in our method, the context will be taken at where the X is written, but with type checking after desugaring, which we must be correct with respect to, the context is taken at the use site. With this gamma, it is still probably fine because you know the standard typing context just grows with more and more bindings. So there is, I just said there is a sort of like a hygienic thing here. So we can. We know its meaning just from where it is written, not at where it will finally reside. So if there is a mismatch between the contexts for both sides. So to ensure that things are correct, we probably have to make the type checking after desugaring a bit hygienic to make them match. And at first it appears just like a normal hygiene problem. We just rename things, and but things get complicated because we want to be general over the core language's typing context. They may be not just bindings. And it will appear, for example, we want to build more contextual sugars upon the language extended with pipes and holes. And now we know that that language with pipe and holes has two typing contexts, a gamma and a delta tau. And the delta tau thing, it simply just can't be renamed. There are no identifiers in it. So here's a example. I won't go over the details, but these sugars build upon the language with pipes. So it desugars to like a pipe and a hole, and early typing would link the pipe with the hole always. But the programmer can also write pipes and holes. For example, they can write code with the yellow pipe and the yellow hole. And then if we just desugar it, we can see that the yellow pipe and the yellow hole intercepts the link between the red pipe and the red hole, which come from desugaring. So this is different from what we would expect from early typing, and there is nothing to rename. So our solution is a bit technical. So think of this is the piece of code on the last slide, and it's written in a tree form. And we see that delta tau, the context for pipes, it indicates where the nearest pipe is. So for example, see the two green dashed arrows. Like if you have a hole at the lambda x of int there, it will find the nearest pipe on the red pipe, and if there is a hole on the right, it will find the yellow pipe on the in the middle. So we can think that during typing, there is a typing context at each location of the syntax tree. This is what we would think of normal typing. And to imitate how early typing works, we introduce anchors. So each construct may now point to a location in the tree where it wants to take its context. So most of the construct will point to itself, so it's just still normal. But as the red hole is written on the right-hand side of the red pipe, it will point to the location there. And following the green dashed arrow there, it will just magically point to the red pipe. So everything is linked as expected. So this is still actually only a partial solution to the problem of hygiene of general context, but it is enough for us to formulate the correctness criteria for early typing and our inference algorithm. So the overall picture of the correctness looks like this. So programmers don't need to know about anchors whatsoever. They just write normal terms in the surface language. But the normal terms of the surface language desugars to anchored terms of the core language. And then the normal terms of the surface language are type checked with our inferred rules, which are sound with respect to anchored typing of the core language anchored terms. And anchored typing, it's just like sometimes a construct just have an anchor pointing up, so it takes the gamma over there. It's actually quite routine. And the point of why this is not complete is actually very simple, because we are a bit strict. We type check the delta, but the delta in the real world, it can be just dropped. The desugar code may just not contain anything related to the delta, so we are simply not complete. But I think it is desirable because we disallow the sugar to just put any ill-type thing in the desugaring context. And then to evaluate the anchor terms, for example, we can probably reduce them to normal terms of the core language. And this can happen if, for example, the core language typing context is just like kind of like a gamma of bindings. So we can use normal hygiene things, just rename them. OK, to sum up. First, we introduced contextual sugars, and they can, for example, do remote linear actions and allow scattered desugarings. And we try to resemble syntax parameters. And we provide an algorithm to infer typing rules for a class of contextual sugars. The steps are context fusion, which introduces desugaring context into the surface language typing context, and early typing to type check things passed down early. And it preserves abstraction. And to formulate correctness, we introduce anchors, which is a technicality the programmers or the sugar authors don't need to understand them. It's just used to deal with the problem of we call hygiene of general contexts, and we use it to formulate soundness, which is proved. And that is all. That's all. Thank you.
Thank you. We have 5 minutes for Q&A. Any questions? Yes. Okay.
Sorry for launching into a maybe basic question.
Okay.
If you go back to the very early, the pipe modeling.
The pipe.
Yeah, so this one, right? Okay, yeah, next one.
Here, pipe.
Yes, so it looks like what you're doing is basically an evaluation of like a programming language with lambda abstraction using explicit environments. That's the delta. And could you basically leverage that you already have lambda abstraction in a setting where you want to work with hygienic macros, basically deep binding, and model this not as a let x equals abc in x plus x concatenated with x, but as abc piped into lambda percentage time dot, and then the right hand side, right? So so basically you have this as a higher order abstract syntax. The lambda would be a higher order abstract syntax, and then press the button for type inference for that, because the lambda then hopefully would be processed by type inference by existing methods. So basically leveraging that you already have lambda abstraction and type inference and type checking for that.
Yeah.
Instead of just going through the way of having environments.
Okay, I think it is very reasonable. And even, like for example, without higher order abstract syntax, we can work with like functional piping. Like we want the programmer to explicitly write lambda x dot x plus plus x. This is also fine, but this is just an example to show how contexts may work. And regarding the higher order abstract syntax, I think it's a very, very, very valuable opinion. I did not think about it, and I will try to think about it later. Thank you. I think very good. It's very good. And actually, we can think of this desugaring as like a meta function, and in a sense, it's similar. I just didn't think of higher order abstract syntax. It's a very good suggestion. Thank you.
One question is that also this example is very complicated. Also, do you have well? For me, it looks like your theory is treating just this kind of things. Do you have any other good example for contextual sugar?
Probably this is quite general, and for example, they can treat things like this. I think this is very well known, and yes. So we basically just add context to pattern-based sugars, so they are still simple, but like very simple meta-level calculation can be supported, but they can probably not very complex. It has to be compositional, as I didn't say, but these are all compositional. So there is a limitation, but just we add contexts.
Okay, thank you very much. Let's thank the speaker again. So the next talk is talk about short paper presentation, and the title is not short, but the title is S4 model secant calculus as intermediate an intermediate language, and the talk is given by Jean.
Yes, Jean.
Jean, yeah, please.
Okay. Yeah. So hello, and I will talk so about SO modal logic and as a sequence calculus for it as an intermediate language. So in the programming language community, there has been a long-standing debate about the place of continuations. And in 2019, so there was this paper compiling with continuation or without whatever, in which the authors developed an intermediate language in which they have the second-class continuations, those are special continuations which cannot escape the scope, a C operator, like for license, which implement double negation elimination, and a CPS translation that erases this operator. And they advocate for a syntax in which we can mix direct style and continuation passing style in the same language. And they showed that the notions of continuation they used in compiler intermediate language is different from the one we usually see in logic. So in logic, continuation are either used linearly or without any restrictions at all. So linearly used continuation corresponds to intuitionistic logic, and without restriction is classical logic. But in compilation, continuation are the second class, and in some sense intuitionistic, because adding those second class types and even a C operator restricted to these continuations does not increase the logical power of the first class fragment. So we studied the calculus to see exactly what is a second class continuation from a logical point of view. And so what exactly is a second class value? So these are values which cannot be returned from a function. They also cannot be referenced from a first class value. And in a language with mutability, they cannot be stored. And this ensures that second class values can be allocated on the stack. So for example, here this is the code a programmer would write. A big is a big expression. And it is then compared to this code. So we introduce a C operator, which introduces a continuation which is second class. We allocate a new continuation J, but it's a continuation, so it goes on the stack, and the big expression is only allocated once. We use it, and then when this code returns, the stack gets freed, and the big allocation is freed. Yes. Also, recently there have been lots of sequence calculus based intermediate representation for compilation, and those allow to manipulate continuation directly. So for example, there has been this paper about sequence core, so it's a compiler intermediate language for GHC based on sequence calculus. This paper used also compiler for sequence calculus based intermediate languages, and this one used specifically the fact that duplication and weakening rules are explicit in sequence calculus to implement reference counting. And so we showed that the calculus of with continuation or without whatever had in fact a sequence calculus. Because, for example, in the CPS translation, they separates functions returning something from functions which doesn't return, so jumps. And the rules of the CPS translation for lambda abstractions is different in the two cases and correspond exactly to the rule for introducing either arrows or negations in sequence calculus, based on if it returns something or not. And so in my master's thesis, I designed a sequence calculus, so a sequence calculus based language, so it's based on system L or mu tilde calculus. And we can interpret the language into mine, so system L-pole box, and we can interpret system L-pole box back into the language, but without the C operator. And this translation factorizes the CPS translations. So it's exactly in the middle point. My calculus is polarized, so it supports both call by value and call by name. And first class types are represented by using a modality box, which follows the laws of S4 logic, almost. So we have the usual rules of a common head, but the strongness is not totally valid because we have to introduce a polarity shift. So it's like adding unit implies B for the arrows is that. And this is because modality and call by value is very difficult together. And so why did we introduce this modality? Well, it's because to introduce a value, a first class value, we restrict the context so there's only first class type in the context. And to introduce values of model types, to introduce a model formula, we also restrict the context so there's nothing on the right and only formulas of model formulas on the left. So it's exactly the same thing. And also, so in a polarized sequence calculus, polarity represents evaluation mode. So there's a positive polarity for call by value and negative polarity for call by name. And since we want model types to be evaluated differently from non-model type, we introduce a new polarity for them. And in this semantics, what we want is that model values go on the heap and non-model values on the stack. So we can combine types, and types have polarities too. And for example, a product of two types, the pairs, are model if both components are models or only call by value else. And so, yeah, we designed machine semantics with the same properties as the one with concentration or without. So model values, so first class goes on the heap, and everything else goes on the stack, especially continuations. And so in this semantics, when the evaluation of a model term returns, the stack shrinks up to the stack how it was before the evaluation started. So this is implemented in this rule. So if we evaluate the value v against the continuation alpha, we retrieve the continuation associated to alpha, and we evaluate v in this new environment. But the stack shrinks up to alpha, and we drop everything allocated after alpha. Why is that sound? Because S has been allocated before, so it's good, and V is a model value, so all its three variables are themselves model, and so they have been allocated in the heap. And we retrieved exactly the stack discipline of with continuation or without, whatever, because when function returns, when returning first class types returns so the model types, well, it's an evaluation of a model terms, so the stack shrinks. And if a model argument is passed to a function, it is evaluated first, and so the stack can shrink after its evaluation again. However, we allow functions to return non-model types. And in this case, things does not go that well. And values are still allocated in a stack-like manner, but this stack doesn't correspond to the evaluation stack anymore, to the call stack anymore. Because, for example, in this function, in this code, y is allocated on the stack if x is non-model. But if the stack shrinks at the end of the evaluation, then it gets returned and dropped, so it doesn't work. And so, yes, the call stack is different from the stack in which we allocate. Okay, so in the title, I also spoke about intermediate logic. So the intuitionistic S4 logic has always been applied to compilations, but here we use really classical S4 logic. But at the same time, we expect intermediate languages to correspond to intermediate logic, that is, to be slightly weaker than full classical logic. And this is true if we restrict our calculus to the fragment in which functions return only model types. But how are we stronger than intuitionistic logic? Thanks to the Gödel-McKinsey-Tarski theorem.
because this theorem says that intuitionistic logic is isomorphic to some fragment of S4 model logic, and this fragment is included into the fragment in which functions return only model types. So we really have, through the Curie-Howard correspondence, a logic which is between intuitionistic and classical logic, and which correspond to intermediate language. And so, yeah, what would I do later? Well, try to better understand the fragment of S4 in which we have efficient compilations, and maybe introduce a dual modality of S4, so the lozenge, because it plays nicer with negations, and try to apply that to efficient compilation of dependent types, and to designing dependent type series between intuitionistic and classical logic, because we know that if we have proof-relevant classical logic with dependent types, it's not sound, but maybe there's a design space between full classical logic and intuitionistic logic. Thanks for your attention.
Questions, please. Any question?
Actually,
Just a moment. Yes.
this is a very basic question.
Yes.
Is this on? Oh yeah, it is. Okay. Very basic question about polarity in this. Does the polarity come from the there's two senses of polarity that are out there. There's like the sense that I know of that is like Paul Levy sense from call by push value.
Yes.
Which seems more like what you're talking about.
Yes.
Okay. And then there's the other sense from like the invertibility of rules in sequent calculus. That might not be.
Actually, they are related.
They are related, yes.
Yes. But here we're not talking about, the different polarity of push values and the evaluation modes. So, yeah.
Okay, yeah, that was my question. Thank you.
Yeah.
Could you say a bit more about how you think this will help with efficient compilation of dependent type theories?
Yes, because if we extend this language to dependent types, we can handle better CPS translation of different types, and so it might be more efficient.
Mm-hmm. And do you see obstacles there? Or do you think that's going to be easy?
Actually, there have been some work called TPS translation for dependent types, which I don't remember well. But I think they have like special rules for type checking continuations. If we may remove these special ADAC rules to have like only logical based rules for, at least for the model fragment.
Great talk. Can you go back to the first page where you introduce the axioms of model logic?
This one?
Yep. So there is a up double arrow.
Yes.
In axiom K.
Yeah.
I didn't see it like in the following definition of syntax. Could you say a bit more about it?
So yeah, you mean here?
Yep.
Yeah. Okay. So it's a negative shift. So it's like unit implies B.
Unit plus B. Why do you need it?
Well, so I don't know.
Why do you need it?
Okay, I need it because to introduce the rule for introducing a box only takes values, but this is a result of applying a functions. So if I will implement, I apply a function, and so I cannot just put it in the box. And if I say let x equal so application of this to that in box of x, then it's not well tied because x is a free variable which is not of model type. It's of type B. So we have to delay the computations and put it into a function.
Okay, makes sense, thanks.
You say this is really S4 logic.
Yeah, so that's the question. In other work, for example, in the Ox-Camel paper, they also have the same kind of limitation. But in a paper of Curien, Marcelo, and Guillaume here. They actually have a same kind of modality, but they say that so they have an exponential modality which they decompose as something like this, then that. So maybe the real S4 modality would be box upshift of B, but I have to look at it further.
Thank you very much. Let's thank the speaker again. Yeah. Yes. Yes. The last talk of this session is about epistemic logic for polyglots, and the talk is given by Luis. Yep,
Yeah, so good morning, everybody. My name is Luis. I'm a student of Chris Martin's over at Northeastern University in the US, and I'm going to talk about some ongoing work in what I think is a good logical foundation for what I call polyglot programs, which is a type of multi-language programming. And I want to start with an example. So I want to take like 10 seconds to look at this example and for people to guess what will happen. Okay, 10 seconds is up. So it's going to crash. And the reason why it'll crash is because I'm splicing in this string blue value into this shader code, and the shader code's expecting a float. So it's going to scream and say blue is not a float. But the problem with the problem here is that this would type check. This would type check just fine. This is TypeScript. It'll transpile, if that's the word that you want to use. And it'll be like, this all looks okay to me. These are valid strings. It's fine. What's the problem? And it's a problem because like this is an error. This is going to introduce a bug, and we don't want bugs. So this example is not pulled from the air. It's adapted from the MDN, which is a popular resource for people who learn about web development. The real example is actually worse. I have a link to it if anybody's interested. And it involves GLSL, HTML, and untyped JavaScript. It's terrible. So we can surely do better than that. But before I start talking about how to do better than that, I just want to note that this is a common pattern in building complex software systems. I'm going to call these polyglot programs, where you're embedding different languages into a single system. These are arduous to test. You can imagine from writing that code, you write the code, it type checks, it's fine, and then you have to test it, then you have a runtime error, then you have to fix it, and you go through this cycle over and over again, and that cycle sucks. So again, we can do better than this. And some of you are sitting there screaming in your heads, make a better static type checker. So clearly TypeScript is not good enough. Okay. And if you are thinking that, then I'm glad you're here, because you're thinking about multi-language computation. And this is the study of systems composed of different languages. So like form function interfaces, compilers, DSLs, and polyglot programs. And we're all concerned with static and dynamic safety guarantees. I'm clearly concerned about a very simple static guarantee, which is, well-typed programs won't go wrong. So there's plenty of work in this space by plenty of people who are worth mentioning. I see at least one person who works on this type of stuff in the room. There's so many of y'all out there. But the thing is that I noticed is that as far as I know, we haven't really talked about a logical explanation of these types of programs. And I find that very interesting. I come from the sort of tradition of Frank Fenning and folks like that. It's kind of a different style than the folks who talked right before me. But regardless, what we're interested in is this sort of query-Howard correspondence and thinking about how to use a logic to give rise to a static type system, calculus for programs, and to understand the essence of some sort of phenomenon. And in particular, I'm interested in taking a natural deduction system and an intuitionistic logic and putting it through the CH pipeline and getting a functional program. So my proposal is to use epistemic modal logic as a way to explain these types of programs. Epistemic logic is a logic about reasoning about agent knowledge. Agents, in this case, we're going to think of them as stand-ins for languages, and epistemic types are going to be for foreign code, or these code in those languages. So before I lose anybody in the rest of the talk, because I'm about to get technical, I just want to share the key ideas here. So first of all, I'm going to introduce the epistemic S4 as a generalization of Fenning-Davies as S4, which is not the same as the classical S4 that we just heard about. Then I'm going to interpret epistemic logic as a calculus for this polyglot programming. And then I'm going to show a small tweak to the calculus where I kind of break my own rule and make something up that goes outside of the logic to get to something that I really want, which is splicing into foreign code. Okay, so the epistemic logic S4. It's pretty small. I mean, so we have our agents, which are just going to be represented by symbols. We have propositions. We have an atomic proposition P, and then we have this box K thing. This box K thing is going to be pronounced box K of A. And it's a lot like Fenning and Davies' box, for those who are in the know about Fenning-Davies' judgmental S4. We have two types of judgments. One is that A is true, one is that K knows A. We're going to have these two contexts that are going to carry things with these two judgments. And K knows A, again, is very similar to this notion of necessity or validity from that Fenning-Davies paper. We aim to prove judgments of the form under epistemic hypotheses gamma and truth hypotheses delta, C is true. And I can take that syntax, put it through our Curry-Howard pipeline, and come up with my typing judgments. And the one that I want to highlight, of course, is this K knows A judgment, which I'm going to continue to pronounce K knows A. That's the more exotic judgment here. Everything else is pretty standard. Normally, I would give the rules for epistemic S4, but I don't have time, so I'm just going to give the vibes. So first, knowledge is like validity or necessity from the perspective of an agent, is the way that I want people to think about it. To prove agent knowledge, we need to depend only on that agent's knowledge. So we're going to use the so-called knowledge restriction. And this echoes Fenning-Davies' notion of validity in their introduction rule. And agents can only know true things, and this echoes this hype star rule. And hopefully, when I talk about the polyglot version of this, we'll see echoes of that again. I'll highlight when that comes up. Okay, so I just finished talking about Fenning-Davies' S4 and the epistemic S4 and how they're related. And in fact, I argue, well, if you have epistemic S4 with a single agent, it's just Fenning-Davies as S4. So surely we get something with multiple agents. And the main idea is to think of multiple agents as being multiple languages in the system interacting. So we're going to reinterpret epistemic logic as a calculus for glue code. And we're going to think of agents as foreign languages. And the glue code will be the way that they intermediate. So for our types, I'm going to have A denote glue types. I'm going to have a blue tau denote foreign types. And then I'm going to have this A tilde K tau thing, which is pronounced A acts like K's tau, as a type translation. It's a user input, and credit where credit is due, I stole it from Patterson et al. They're colleagues of mine at Northeastern. Thank you so much. I'm staring at the camera. Thank you. So next is our contexts, reinterpreting the knowledge context to now map directly to foreign types. And then the foreign context will be used to type foreign expressions. Then we have another mapping. I'm overloading the tilde, and it's going to be pronounced map gamma to case phi. It kind of has a mechanical flavor to it, and it's defined inductively by these rules. And the one rule that I want to highlight is this one over here, which shows that if I have a target agent and the type is mapped from an agent that's not the target agent, then I'm going to drop that, right? And so that's sort of the knowledge restriction that I was alluding to earlier. We're going to see it being used. We're going to work with two judgments. First is the glue typing, which is the standard judgment that we saw earlier. And then we have our foreign typing rule, which is saying under language K, F will be typed at tau. Okay,
So our introduction rule requires foreign expressions to type check. First of all, it's this over here, and notice that what I'm doing is I'm embedding the foreign expression directly into my glue code. So it's almost like quoting if you're used to that language. And I'm doing this knowledge restriction that I was talking about here. So I am using only the knowledge, you can think of it logically as I'm using only the knowledge of K to prove statements about K's knowledge. The elimination rule allows us to permanently reuse knowledge. If I have box K of tau, then I can continue on with K knows tau. And then our variable rules are here. So the one on the left is a standard variable rule that you would see from a lambda calculus. And then the one on the right now requires types translation. And it's saying if K knows tau, then we can assume A. And this is to say, if you imagine tau to just be A, then you can think of it as K knows A. Well, like I said, agents can only know true things. So if an agent knows something, then we can assume it's true. And that's what that is. That's what that is. So let's take stock of where we're at. I reintroduced the rules of epistemic logic. I have agents as foreign languages, epistemic language as glue language. Okay, I should be done. So I'm going to rewrite my example here. And just real quick, does this seem right to y'all? Just real quick. Okay. It looks okay, but it's not quite right. It's a valid program. I promise you it type checks, but it's not quite right. And the reason for that is that my original example had parameters for vec4 over here, but there's no splicing going on. And you might think like, well, you didn't use, there's an entire expression you didn't use. Well, Lightbox won't help us here. And the reason why is that Lightbox lets us extract from foreign code, but it doesn't let us go the other way around. And I really want to go the other way around. So how are we going to do that? We're going to just tell agents information. Bless you. We're going to just tell agents information. It's a pun on let, I swear. It's just let backwards because it's a let binding. And what it's saying is if A is true and A acts like K is tau, then I can tell agent K about tau. It's almost like I'm telling K something in their language. So we can rewrite our example. If you let me put in a regular let binding in there, this would be our rewritten example in our language, which is great. And here's a 3-language version if you don't like the regular let binding, if you want letbox being used. There it is. And this red language over here introduces 0.8. And then you can imagine some substitutions happening and ends up there in the yellow language. The thing that I think is cool about this is that you can imagine language B, or the red language, being a little bit more complicated and allowing for user inputs, for example. So a user can like customize their shader code or something like that. For beta principles, this first one comes from a local soundness analysis. So if you've looked at like the judgmental style of doing logic, or like Fenning-Davies' work, then they talk about local soundness. I don't have time to get into what that is, but just know that this kind of comes from a local soundness analysis. There's a substitution principle in use being here. But the one thing that I want to point out is that we have to translate from foreign code to glue code here. Next, we have tell. This is a more speculative rule. It doesn't come from any analysis. I had to pull out from the logic to do this. But there's this back translation here. So I think of it as sort of the inverse of what let is doing. But now we can run our example in totality. So we're just going to map floats to floats. There's our example from earlier. Here's type checking. It's hideous. Don't worry too much about it. Just like you can read it as sort of like I'm exporting from the red language, and then I'm injecting into the yellow language. Same thing with the operational rules. It's just a series of substitutions going on. And one thing that's worth pointing out, 2 things that are worth pointing out, is it's kind of hard to see here, but there's this like double translation thing that's happening here with tell, and I just want to be upfront with that, with saying like this is a what's the word? A limitation of tell as it's being used. Remember that tell had a translation going on, and hype star also has a translation going on, and it's hard to see because this is really tiny. But hype star has a translation, and then tell has to do a translation, so I'm double translating, so that seems to be a problem. And then the next problem is, all right, you have a box expression, what do you do with it? I don't know yet, I'm still working on it. Fenning and Davies would say no computation under a box, and that made sense for their staged computation application. So we're still working on what to do here. All right, conclusions and future work. So we developed the epistemic S4 natural deduction system. We kind of reinterpreted it and gave an analysis of polyglot programming, and then we extended it with the tell expression. And on the horizon, we of course want to think about foreign languages with different properties, parametricity effects, so on and so forth. We want a logical account for tell. One reviewer very helpfully mentioned adjoint logic, and we want to look into that. And last is details on expression translation. One reviewer asked, like, do we even need it? It seems hard, and people don't like thinking about it very much. And we did also question, like, can any of it be automated to make this a usable system for people? And that's it. Yeah, thank you so much.
Questions?
I'm a little bit confused about the philosophical setup here, because it seems like there's a bunch of different things that could be called polyglot programming. Like you gave the example in the beginning with like HTML, JavaScript, GLSL code, and then there's like staged programming, and then there's FFI, and these all seem like very different to me. Like for instance, in staged programming, you're generating code that goes into a compiler.
Yes.
And so, but whereas in FFI, like you're calling other code that's been precompiled, and then in the HTML and JavaScript thing, like HTML and JavaScript are like completely different language paradigms. So like HTML doesn't have let bindings.
Mm-hmm.
What in this fairly large space of things that could be called polyglot programming, like which one is your thing?
It would be the last one. I maybe wasn't very clear with that.
Staged programming?
It would be specifically the situation where I'm sort of quoting foreign code in my code base.
Okay.
So I guess that's more similar to stage programming in philosophically, but.
So then why is, maybe this is more of an in-depth question, but why is that agents? Because that seems like there's a clear hierarchy of like, there's a host language that generates that generates code, but it's not like they're not on equal playing field the way I would think agents are.
You mean the agents have a hierarchy?
Or just like there's a host language, and then there are target languages.
Yes. Yeah, so the host language, yeah, there is a hierarchy. The host language is sort of on a higher plane than the
host language isn't an agent.
The host language is not an agent.
Okay.
Yeah. Actually, it's the other way. It's more the agents are on a higher plane than the host language. And the adjoint logic picture for this would actually make it much simpler to think about. So if you want to talk about it more offline, I'd be happy to.
Thanks.
So I think it's time. Yeah. Thank you.
Welcome back after break. I know it's a long way. Well done for making it back. So this is the second session of PEPM'26, and we have 4 talks. And the first one is going to be given by Sean Harbaugh, who is going to tell us about computation tree semantics.
So yes, thank you very much for the introduction. So in this joint work between myself, Sean, and my PhD supervisor, Hans Hüttel, we have been developing a new approach to describing inference rules, which we call computation tree semantics, and wherein we capture the algorithmic aspects of these structural inference rules. So when we define the semantics of a programming language, we commonly do this using what is called an operational semantics. And these come in 2 styles. There's the big step style, or also called a natural semantics after Kahn, and there is the small step style, also called a structural operational semantics after Plotkin. Each of these have their own advantages that stem from one fundamental key difference. The first being that big step rules, as you see over here, describe one complete computation in one step, so to say, whereas small step rules over here describe a single computational step in a bigger computation. As a consequence, the big step rules are often less numerous and also slightly simpler compared to the small step counterparts. But the small step rules have an easier time describing certain features or program features such as non-termination or parallelism. Another advantage of the big step rules is that they are more resemblant of how someone would implement an interpreter, so using a big step semantics gives a more natural transition from specification to implementation. Due to their distinct advantages, there has been a lot of work on reconciling the two styles by deriving one style from the other. In this line of work, we typically see the big step to small step conversion as the more challenging direction, and this is also what we've been working with in this work. So we've studied a range of previous works working with this big step to small step conversion, and some of them use very similar, some very different approaches, but there is still one key thing they all have in common, and that is, first, they use the premises of big step rules to break the big step semantics down into small step rules, and then we chain these small step rules together by some notion of memorization. And some typical approaches we see here is to use a stack of continuations or a continuation passing style to do this memorization. With computation tree semantics, however, we take a slightly different approach and try to capture as much as possible of both the big and small step aspects of a semantics as possible, thus giving us the best of both worlds, but without the need for converting from one style to the other. The core enabling data structure that allows us to do this is the computation tree. And you can see 2 examples of computation trees right down here in one full example of a step in computation tree semantics. So as you can see, steps go between these computation trees in contrast to a normal small step semantics where the configurations are flat, so to say. So one key property of these computation trees is that they directly encode both evaluation contexts and continuations. And in the example down here, we can, for example, see that the expression 1 plus 3 plus x is being evaluated in the context of sigma, and we're currently memorizing the value 1, which was established at a previous step when evaluating the first constituent 1, seen out to the left. Now, 1 plus x plus 3 has itself gotten to the point of evaluating x plus 3, the left constituent, and x plus 3 is again evaluated in the context of sigma, and we're memorizing the value 2, which will have been established again in a previous step when evaluating x. Finally, x plus 3, as seen in the top, has gotten to the point of evaluating the second constituent 3, and it is being evaluated in the context of sigma, but we have not yet established the value of that literal 3. So this is where we start to see continuations, because the only way to progress from here is to continue the evaluation of 3, because the 2 previous nodes in the tree are still waiting for the sub-computations or sub-goals to be completed. Thus, in one step, we can establish the value 3 of the literal 3. And after this, the annotations such as add2 down here tell us what to do with the values of sub-computations. For example, for addition to proceed, we'll have to add 3 and 2 together, but you'll see this shortly. So another important feature of these computation trees is that they preserve the full unchanged syntax of whatever program or expression is being evaluated. And you can always, by looking at the root, see that complete syntax. And this plays 3 key roles. First, it gives the computation tree a structure that is similar to big step derivations, as you will see later, and is important for capturing the big step aspect of a semantics. Next, since we always have the full syntax, we know exactly which parts of the expression or program is being evaluated, and this helps us capture the algorithmic aspects of a semantics. Finally, by using these computation trees, we can capture the small step aspect of a semantics, as you could see here in a stepwise restructuring of this tree, but at the same time, we can actually describe this behavior using rules that follow a mostly big step-like structure, as seen right over here. So to see how these rules work, let's try to evaluate a simple expression x plus y. So the addition rule, perhaps it would be easier if I just point with the cursor. Would that be better? I'll just do that. So over here, the rule states that to evaluate any E1 plus E2, we must start out with a computation tree node that contains a sigma in what we call the primary component and the empty secondary component. And here it's probably easier to just point. That is also what we see up here with CT1. X plus y is evaluated in the context of sigma. So next we proceed by matching the secondary component from the current computation tree, which is CT1 currently, with the patterns that you can see right down here with add1 and add2. So these are clauses, and since the secondary component is empty and add1 has the empty pattern, add1 is enabled. So to proceed from here, add1 tells us that we need to evaluate E1 given the state sigma to some value n1, and this implicitly happens in one or more steps. So initially, to initiate the evaluation of add1, then we grow the computation tree into the constituent up here corresponding to E1, which is x in this case. And then that concludes the entire initial step for add1. Next, we can then use the variable rule, which you see down in the corner, to state that x can evaluate to some value n1 by a simple lookup in sigma. Now that we have established the value n1 of x, that is the same as having established the value n1 here in the addition clause. So the way we then proceed is to update the primary component, as seen over here, to the same sigma, but update the secondary component to store n1, the value we just found, and that is what we see in computation tree 4. Now we can evaluate y in a very similar manner. We grow the tree into y, we establish the value n2, and then, as per the rule add2, right, sorry, I forgot to mention, now that the secondary component contains n1, we have enabled add2 because n1, it now matches the pattern in add2, and therefore we can evaluate E2 to N2 and produce the final result N1 plus N2, as we see here with computation tree 7. So now that you have seen how these rules work, we can also observe the correspondence between a big step derivation and an equivalent CTS transition sequence. So here we have the same transition sequence and an equivalent big step derivation. And in the root of the derivation, we can see that x plus y is evaluated in the context of sigma, and that is what we see in CT1. Furthermore, the root node over here says that x plus y evaluates to n1 plus n2, and that is what we see in the last computation tree down here. Now, these subsequences for evaluating x and y then follow a similar pattern where we have two corresponding computation trees for every big step derivation tree node. Furthermore, we have a similar nesting structure, so to say, where here we can see that x is the child of x plus y in a similar way as x is a child of x plus y right over here. And this becomes important later. So an easy way to see how this works is to see the computation trees as partial big step derivations, where the computation tree essentially grows up through the big step derivation until we establish the value of some constituent, and then we pull that value down towards the root. So n1 is pulled down, and then n2 is pulled down, and when everything goes to the root, we have the final result. So now that we have seen this correspondence, we can also start looking at the conversion from big step rules to computation tree semantics rules, or CTS rules. And here we use a similar approach as to previous works, where we essentially take the premises of a big step rule and then turn them into their own clauses in a corresponding CTS rule. Furthermore, the left-hand side of the conclusion becomes the rule head, as it's called, and the right-hand side becomes the terminal result of one of the clauses, in this case, the second clause. Finally, we use the secondary component to store the value n1 of e1 so that it is remembered at a later point in time. So this is just this is just part of one example that we have in the full article, where you can see the full conversion and also see a full equivalence proof that proves that these two are in fact equivalent. But I'll show you an example of that later. Furthermore, an important thing to note is that whereas CTS imposes a strict evaluation order, E1 first, E2 afterwards, then this order is not actually imposed in the big step rule. And therefore, we could easily also have created a CTS rule where E2 was evaluated first. But here we just picked to evaluate E1 first. Now, going up to a slightly more complex example, we also cover an example where we transform Launchbury's big step semantics for the call by need lambda calculus into an equivalent computation tree semantics. And here we see an example conversion for the application rule. We follow a similar pattern to before. Each of the big step premises become a clause in their own clause in the CTS rule, and the conclusion becomes the header and the final result, and so on. But here it's important to note that the heap gamma, which shows up over in the big step rule here, is updated to delta throughout the evaluation of that rule, and that must be mirrored in the CTS rule. So first, when we evaluate, the header up here, gamma, always refers to the primary component of the current CT node, or the current computation tree node that we're looking at. So initially, gamma up here will correspond to the gamma from the big step rule. And when we evaluate app1, then gamma up here corresponds to the big step gamma. Now we produce an updated delta and store that delta in the primary component along with the value set, which means in the next step after that, gamma from the rule header will now correspond to delta from the big step rule. And thus, when we evaluate E prime over here in gamma, that is the same as evaluating in the context of delta from the big step rule. And then everything just follows in the same way as before. Again, you can see the full conversion and full equivalence proof in the article, but I'll show a small piece of the equivalence rule for the lambda calculus later. Finally, for the third example that we also covered in the article, we have the semantics for the while language, and here we also see the example conversion for the while rules. So again, the primary components essentially become their own clauses in the corresponding CTS rule, and we thread the updated primary component through the rules, as with the previous two examples. However, now, since we have two judgments over here for evaluating the loop condition, and these are essentially equivalent, we can just put one instance of that judgment in the CTS rule and use the secondary values to match on whether we're following the false or true branch. If the condition evaluated to false, we just output whatever sigma that we currently have, but if it evaluates to true, then we can evaluate the while body. Now, after evaluating the body, we update the primary component and go back to the empty secondary component. And this is interesting, because this re-enables while E, which means we can again evaluate the loop condition and possibly also the loop body, thus giving us an iterative behavior which is actually described fully compositionally in the program syntax, which is not actually possible in either big step semantics or a small step semantics. Now, moving on to how we prove equivalence. Here we can use the correspondence between a big step derivation and computation trees that we saw in a previous slide. And yes, as mentioned, you can see the full examples in the article, but here I'll just show you a small part of the proof for the lambda calculus, where we prove the two semantics equivalent in the manner stated right here. So starting off with the lambda rule, the lambda abstraction rule, this is quite simple. Both the big step semantics and the CTS evaluate some heap and lambda abstraction to the same heap and lambda abstraction. So the proof is immediate in both directions. The application rule is a bit more complex, however, but still fairly simple. So if we start in the direction from big step to to CTS, then first we assume that we have a big step transition for some application. And from that we can then infer that we must have transitions for the constituents E and E prime. Now, by using the induction hypothesis, which we have up here in the top, we can deduce that we must have equivalent CTS transition sequences that describe the same evaluation for E and E prime. So far, so good. Next, we can use the compositionality of computation trees to essentially wrap these two sequences, sec1 and sec2, in the application of the clause app1 and app2 from the CTS rule for application. We can do this because we have proof that E terminates and E prime terminates, and they must still terminate even if they are a subcomputation of some bigger computation. And at this point, we can just chain these transition sequences together to produce a full transition sequence for the evaluation of this application. In the opposite direction, going from CTS to big step, we just do the exact same thing in the opposite order. Break down the full transition sequence into sec1 and sec2, use the inverted induction hypothesis to get the premises of the big step transition, and then finally prove that big step transition. Yes. So up to this point, you have seen how we can use these rules to compute the value of an expression. But CTS captures the algorithmic aspects of inference rules in general. So we can also use CTS to describe how to compute the type of an expression. And so here we can see a simple example where I have added booleans and where we have a simple language with booleans, numbers, and addition. And the type rule for addition tells us to evaluate the type of E1, of E2, and we memorize both of these, but only if the resulting types were both net will there be a well-defined step saying that E1 plus E2 has the type net. If either of the constituents had the type bool, there would be no well-defined step and the expression would be ill-typed. Furthermore, we can also describe parallelism and non-deterministic choice with CTS. So parallelism can be described by having multiple judgments in a single clause, which translates into creating multiple branches in the computation tree, and there actually making an actual tree. But each branch in this tree has their own valid regex, so we could either evaluate S1 or S2 one step, and the steps could interleave arbitrarily. Next, non-deterministic choice can be described by simply having multiple enabled clauses. So if we start out with the empty secondary component, then OR1 and OR2 would both be enabled, and we could get the result of evaluating S1 or S2, but not both. So what you have seen is computation tree semantics, wherein we capture the big and small step aspects of a semantics, and the key data structure that enables this is the computation tree. We show that we can do a straightforward conversion from big step rules to CTS rules, and through that obtain a small step understanding of a big step semantics. We have also proved that for the 3 cases that we've covered, that the resulting CTS is equivalent with the original big step semantics, and we've also shown you how CTS can capture other kinds of capture relations other than operational semantics or transition relations. In the future, we would like to make this systematic conversion approach into an actual algorithm, so we don't need to do it by hand. And also, we'd like to improve support for concurrency in CTS. So I didn't mention it earlier, but CTS is restricted currently in the sense that the branch for S1, seen right over here, cannot actually affect the sigma stored in S2. So in the future, we would like to add some kind of shared state to CTS. Next, we'd also like to be able to obtain algorithms or even implementations from a computation tree semantics, possibly in combination with a concrete program in the semantics described. Finally, since we can describe both type relations and transition relations with CTS, we'd also like to prove soundness, to prove that a static semantics is sound with respect to a dynamic semantics, where both of them are described in CTS. And as you'll see in an upcoming work, this can actually be done in a quite straightforward manner. So that was all from me. Thank you very much.
Thank you. We have time for a few questions.
Hi, great talk. Really enjoyed it.
Thank you.
This might be more of a basic question, but is it fair to sort of understand the CTS data structure as a way of enforcing an evaluation order for big step operational semantics?
Well, they do encode continuations, so and you can see the possible orders in which operations can be evaluated from it. So I guess that would be a valid way of interpreting it. So so yes, like to evaluate x plus 3, yes, you can see it. To evaluate x plus 3, we must first evaluate 3. And this is, of course, at a point after we have evaluated x. So definitely, the computation tree encodes the order in which operations should be executed. But a big part of that ordering is also encoded in the rules in the CTS rules.
Awesome. Yeah. Thank you.
I think combined calculus needs a kind of special treatment in evaluation context. Can you Can you describe the semantics of call by need calculus in terms of yours?
Sorry,
Call by need calculus.
I cannot hear it. Sorry.
No, maybe. Call by need calculus. Need.
Yeah, call by need and then
calculus. Can you?
Oh, calculus. Sorry. Sorry. So now that I know what do you want me to explain? Just
You write CBN. Is it call by need or call by name? CBN.
Okay. Yeah, that's the call by need.
Call by need. Oh, so you have already done it. Okay.
Yes.
Okay. Thank you. So, did you have any problem in describing that kind of thing?
No, there weren't that much of a problem with converting the big step semantics into CTS. So yeah, we have the example of application. So the primary challenge in this conversion is the data flow analysis, essentially, and establishing the order of premises. So the addition rule didn't have any strict ordering, but here, since we have a dependency between the two premises, then we of course also have an ordering in the big step semantics. And when we then convert it into a CTS rule, then the primary concern is to ensure that the data flow is retained. And yeah, that is where the primary component retains like the current state that we're evaluating in. So yeah, the biggest challenge there would be to ensure that we always have the latest state in the primary component. And of course, automating that conversion would also be a challenge, but definitely doable since we have data flow analysis. There's a question there.
Yeah, thanks, Christian. So the big step semantics has an advantage. I mean, you're alluding to it at the end of making sure to capture what's independent of each other, which sub-computations. So, for example, in linear logic or linear lambda calculus, you could say, like, I'm computing this part with only this environment, and I'm computing the second argument expression with another environment, and expressing that I don't need, I will not touch the first environment in the second one.
Yes.
Can you capture that? I mean, at some point, capture this kind of independence of evaluation order, and also the independence of other parts for computations, in this case, the environments?
Yes, the independence of evaluation order, not so much, because, well, you could evaluate them in parallel, but then you would need to bother with the consequences of two parallel parts of the program, which could complicate proofs. It's like opposed to in a normal big step semantics where you can either take the first case first or the second case first. So since CTS imposes a very strict evaluation order, it's not so easy to capture this independence. But the independence of program parts can definitely be captured. So in this example here, we evaluate S1 and S2 in the same in the same context, but we could evaluate them in different contexts. You could evaluate them in different contexts, and we would be able to reason that, okay, they have different contexts, they don't touch each other. And in the sequential case, then you only have one branch at a time, so only that active branch could affect anything. So in that case, we can also show independence there.
Okay. Thanks, Sean. Right. Okay. Well, moving on to the next talk, which is given by Alex Inotzko. The topic is about lightweight and efficient cloud services. Alex.
Thank you. Writing distributed systems is difficult, even in the case of simple systems. As an example, I will consider a simple system with like 3 nodes that are referred to as locations, L1 to 3. So the traditional way to write a distributed system is just using networking primitives like send and receive. The problem with this approach is that it's very easy, for example, due to mismatched control flow between these locations, to end up with one location running a receive, whereas while like the other end is not sending, or the vice versa, which leads to deadlocks and other similar issues. And the fundamental reason for this is that for each one of these nodes, even though they're part of the same kind of large system, we need to write a separate program that's completely independent. And choreographies and choreographic programming aims to solve this issue. This is a different programming model for writing distributed systems that has actually been around for a while. It's been introduced by the World Wide Web Consortium in 2004, but more recently it has started picking up more pace. Coming back to the example, how choreographies help here is that using choreographic programming, you can define one single big program that encapsulates the behavior of all nodes in the system. So you get like a global view of the system. And choreographies also provide some higher level operators that you can use for communication. So instead of having to choose between send or receive, you can just say in your program that L1 sends a piece of data to L2. And there is an automatic process called endpoint projection, which is going to take this big program and kind of specialize it for each node in the choreography. And it's going to compile down that higher level operator into the appropriate networking primitive at each location. The thing this gives us is deadlock freedom by construction, which is a really useful property to have. So if you write a choreography and it compiles, you have a guarantee that the resulting system is going to be deadlock free. And we're going to be focusing on writing choreographies in Haskell here, which is doable using the Haskell library, which was introduced a few years ago at ICFP. It implements choreographies as a monad in Haskell, so it plays very nicely with the rest of the Haskell ecosystem. And we're just going to quickly go over the Haskell API. The 2 main types are the choreo monad and this A at L type, which represents what's called a located value. So again, a choreography is a global view of a system, but some pieces of data are only going to be available at one node, and they are represented using these located values. And Haskell provides some higher level operators for communication using these located values. For example, this squiggly arrow simply sends a value from one location to the other. So it just takes an A at L1 as input and gives you back an A at L2. The location itself is represented as a proxy because these L's that we've seen so far, they are basically type level tokens, type level strings representing the locations. So the proxy is used to give you like a value level handle to the location. And there's also a locally operator, which this is basically how located values are created. You run a local computation at a single location, and that gives you as output a value at that location. Just to give a quick illustration, here's again a system where we have a value at L1, and using this operator we can send it to L2. And we can notice that its type changes to A at L2. And our work builds upon Haskell, and our motivation is that we want to use choreographies to implement network protocols, because deadlock freedom by design is a great property, and of course we want our network protocols to be deadlock free. And specifically, the protocol we are considering is that of a data clean room, which consists of many clients that wish to perform some shared computations on their datasets, but they don't necessarily trust each other to share the datasets between themselves. So there is kind of like a trusted server in the middle that the clients communicate with, and that one performs the computation and distributes the results. And this can be combined with things like trusted execution environments to ensure security. Here is a kind of simplified diagram for what a protocol like this might look like. So on the left here we have the potential clients, in this case hospitals, and here we have the server. So in this schema, sorry, in this diagram, the protocol first begins by the clients sharing their own data schemas to the server, and then the server is going to compute like an aggregated data schema containing all the columns, and then just distribute it back to the clients. And then each of the clients says what kind of queries they wish to run on the aggregated data. Then there's going to be an agreement phase where a client could say that they don't agree with what this other client wants to run. So the protocol could end here if the clients don't agree. But if they do agree, then they actually proceed to send their data sets to a server, who then computes the queries on the aggregated data and sends the results back. Now, it would be great to implement this as a choreography, but using Haskell and the existing API, the programming model is a bit restrictive because the communication is kind of simultaneously too granular and not granular enough, because Haskell's communication is kind of all or nothing. You either send a piece of data just from one location to the other, or you have to broadcast it everywhere, which we'll see a bit later for branching. And also, Haskell is kind of optimized for running a choreography with a fixed set of participants, so it's kind of difficult to define a choreography that you could run with, today with 50 clients, tomorrow with like 100 clients. So our contribution is called the Cloud Core, which is a set of extensions for Haskell, which adds some new operators and primitives to make these kinds of protocols easier to write. The main new concept we introduce is the notion of a multiply located value, which enables these more complex communication primitives. We will see later how we optimize Haskell's branching with static analysis, and how we make it easier to run choreographies with like dynamic and configurable participants. And lastly, we also formalized the semantics of Haskell and of our extensions to it. So the first new concept we introduce is multiply located values, which basically allow you to treat a bundle of these located values that could be at different locations. This lets you treat them as a single unit that you can then manipulate easier. And using this, we can implement some more advanced communication primitives. And what's nice about this is that this doesn't require any kind of modifications to the core of Haskell. We can just implement it as some extra functions, basically essentially lowering to Haskell's primitives plus some generic programming techniques. So we introduced this new data type, which we just called @@. But this one on the right, instead of having a single location, has a type level list of locations. So a value of type A at LS means that this value is distributed, like basically each location in LS is going to have one piece of this value. And for representing these at the value level, instead of just using a single proxy for one location, we use another generic programming type, this NP, which is basically a heterogeneous list of a proxy for each location in LS. So this is, kind of equivalent to just a list of a proxy at L1, L2, and so on for every location in LS. And using these multiply located values, we introduce a number of new operators. The first one is for what we call one-to-many communication or scattering. So if you have a located value at one location and you want to send it to multiple destinations, using this operator, you can do exactly that. And the output is a multiply located value at those destinations. And you can see we use the NP proxy here to represent the destinations. The kind of flip side to this is many-to-one communication. So when you have values located at, you have a multiply located value already that's distributed across your system, and you want to send all of them to a single destination, you can use this gather operator, which just accumulates them all into a list. And the output here, the type looks a bit complex because it's again using an NP of a weird generic programming type. This one is basically just a list that is guaranteed to have the same length as the length of LS. And tracking this length of the list in the type allows us to later on, with a different operator, send these values back to their origin one by one with this pointwise communication. And lastly, we have a multiply located analog to hash scores locally, which we just call multi-locally, which lets you run local computations in multiple places at once, producing a multiply located value. And using these, you could implement a protocol like the data clean room in a much easier way. For example, all of those, the steps in the protocol where we had many clients sending their queries or their schema to the server and then the server distributing it back, those very nicely map to the operators I've described so far. And once you have that choreography written, it still relies on all of these type level indices, which normally would be pretty difficult to kind of instantiate dynamically. But using generic programming, we can also write some easy to use functions that let you just using a dynamic list of strings, basically turn that into a type level list of locations that you can instantiate your choreography with. Next up, let's look at propagating choice in choreographies in general and in Haskell in particular. Branching in choreographies is a bit tricky because to ensure this deadlock freedom, you have to ensure that every node in the location, whenever there is a branch, they all take the same branch. Otherwise, it might be that in one branch, one location should be sending a piece of data, but because it took another branch, it doesn't. Which means that the value that you're branching on or the decision that you're branching on has to be broadcasted to all members of the choreography. In Haskell, this is done with this cond operator. So here we have a small choreography where at location L1, we are locally computing some data that we then want to branch on. So we do cond from L1 with B, which means that L1 is going to broadcast B to everyone in the choreography, and then they are going to all run this function here with B. And here we have a branch. If B is true, then L2 is going to send something to L3. Otherwise, if it's false, it's going to send something, L2 is going to send something to L4 instead. And what's crucial here is that everyone runs this. Even, for example, if you have an L5 in this choreography that is not mentioned here at all, L1 will still send the B to L5, and L5 will still run this code, but it will just be a no-op. But we still have some network communication overhead here. So we, in our contribution, we also we also try to optimize this. Again, looking at the cond function from Haskell, we see in its type signature that it has the value to be broadcasted, and then the function that every member in the choreography runs. And yes, everyone in the choreography runs this function, even though they might not be involved in it. For example, in a protocol like the one we've seen so far, you might have some error handling where when the client is sending the data set to the server might check that it conforms to the schema. And if it doesn't, it might send a message back to the client. In this case, you don't want to message every other client, for each client's particular error handling. So to make this more efficient, we have to find out somehow who is involved in this function to only communicate the branched value to those locations. And we do this using a technique from partial evaluation called the trick. And coming back to the example, how we apply the trick in choreographies is we basically enumerate the possible values of the scrutiny of the branch value, and we just apply this function to all of those values, collecting all of the locations that we see along the way. And then that's how we can build a set of involved locations. With this, we introduce a new operator that we just called cond underscore, implementing this kind of optimized branching. It introduces the two new constraints on the scrutiny, that it has to be enumerable and bounded, so we can actually enumerate all the values. And there is one more difference here. The classic cond does not return a located value. It returns a regular value, which means a value that's present everywhere, because by definition, everyone is going to run this function, so everyone can build a B. But with this cond, that's the main point of this cond, is that not everyone's going to run this function, so not everyone can build a B. So we cannot just return any value. It's going to have to be a located value, and since the only location that we know for sure is going to run this is the one sending the value, then the output is also going to have to be located at the sender. And lastly, we also provide formalization for the semantics of haskell and also our optimized cond. Note that we don't formalize our other extensions because they just lower to Haskell's primitives. So their correctness basically follows from the Haskell primitives. We proved soundness and completeness of the endpoint projection process, which means that this low-level kind of specialization and compilation step preserves the high-level global behavior of choreographies. And using this, we can show that Haskell and our extensions indeed are deadlock-free. And our proofs are based on the principle of confluence, that if you have a kind of a network system that could reduce some locations in a different order, the order in which it does so doesn't really matter. So to conclude, we've seen how choreographic programming works and how it works in Haskell with Haskell. It provides deadlock freedom by construction, and it can be useful for designing network protocols, but it does have a few limitations. And we introduced Cloud Core to try to address these limitations by employing multiple located values and by optimizing the implementation of branching. And and also we made it easier to run choreographies with configurable participants. And we also provide a formalization of Haskell and of our extensions. With that, I will thank you all for your attention.
For questions?
Have you started to build systems with this? Do you think this is it? Is this the end of extensions for Haskell, or what else is left?
Yeah, we have started building something with it, but I don't think it's the end necessarily. It's the first step. And there's also some, there's also some concurrent work extending Haskell in a few different directions.
Thank you for your presentation. And I'd like to ask if you have a broadcast primitive or something like this, because your primitive explicitly enumerates the participants when you do multicasting. So do you have broadcasting instead?
Broadcasting as in just send it to everyone?
Exactly.
Well, you can use this for broadcasting. So if you make this function ID or pure, you essentially have broadcast.
I see. Thank you for your clarification.
So to clarify, we don't replace this operator, we just introduce a new one. So you can use both in the same choreography.
Thanks for the talk. Distributed systems tend to be distributed because they also have certain, at least crash faults. Can you accommodate a certain crash fault model, particularly when it comes to broadcasting, which is very sensitive to that, or multicast as you're adding here?
Mm-hmm.
How's that, how does it help build crash fault tolerant systems?
Yeah, so that I guess depends on the kind of lower level network layer that you'd have underneath these choreographies. That's something that I think you'd have to fix to implement like fault tolerance at that level.
So I have a question about the use of Haskell. You mentioned the challenges in Haskell you have to address in the library, and what are the benefits of using Haskell?
Of using, Haskell or Haskell?
Haskell.
Haskell,
Yeah.
the language.
Yes.
The advantage of Haskell over other languages is well, first of all, the advanced type system. Like the fact that we can track locations in a type system is not something we could do, or not, at least not easily in other languages. And also the fact that Haskell is a pure language with tracked effects. So one thing I've kind of glossed over here is that when you're running those local computations, you can run some locally effectful computations. But the choreo monad tries to kind of hide that away and control effects, such that when you have a choreography, you can't have effects that interfere with like the network communication and so on.
For your variant of cond on this slide, you said that you collect the list of participants from your functions at first, and then you broadcast to everyone in that group. But that's not reflected in the type of cond. Is it possible with a better type system, better in quotes, to track that within the type of cond? And if you could, would it be useful?
So in other words, to like track the participants in the type, yes, it's possible, and actually there is some work that's doing that, but it's doing that in Haskell is pretty painful. And also we tried to stay, one thing maybe I didn't stress out is that all of our extensions are backwards compatible with Haskell, whereas if you were to try to do something like that, you'd have to change the API quite drastically.
Right. Okay. Let's thank Alex again.
Thank you.
Right. We're coming to the third talk of this session. It's a short paper, so it's going to be 15 minutes, and it's going to be delivered by Masaki Toyota. The topic is about a Haskell implementation of the bidirectional transformation language BEAGLE.
Thank you. Hello, I'm Masaki Toyoda from Hosei University. I will present on this topic. First, in model-driven engineering, synchronization between models is important. One approach to model synchronization is bidirectional transformations, BX. BX is a framework for synchronizing two pieces of information using transformations. It consists of forward transformation get and backward transformation put. Get synchronizes information from the source data to the view data. Put writes back the updated view data to source data while referencing original source data. A BX can be classified according to how they are defined and how to propagate, update. First, definition style. There are get-based approach and put-back-based approach. In get-based, the user defined get and put is derived automatically. Since get is generally not injective, so get-based suffers from ambiguity in the derived put. In contrast, putback-based approaches can avoid this problem. In putback-based, the user-defined put and get is derived uniquely. Next, the update propagation method. There are state-based and update-based approach. In update-based BX, at first use get 0, and thereafter transform the update information using put and get 1. In state-based, each transformation make a new state, so the processing time increases as the size of source data grows. In contrast, update-based BX transforms as a smaller unit updating actions. So when the state size is large, it is expected to achieve shorter the processing time compared to state-based. In addition, update-based has greater expression power. Next, outline. We incrementalize the putback-based BX language bigger. Our design is inspired by elite ranges and update-based BX and BX language X. Next, Beagle is a putback-based and state-based BX language implemented in Agda and Haskell. Beagle provides some core functions. These include the base primitive and these combinators. Each of these has two semantics, for one for get, one for put. For example, skip has function f. Skips get apply f to the source. Skips put skips propagating update from the view data view to the source. We use Beagle implemented in Haskell, the semantically typed language. Due to strict type constraints, it is difficult to mix two different types across all primitives. To solve this problem, we adopted a common generic type, namely val, as both the type of the state and value in update information. It imposes relatively weak structural constraints. In addition to the original constructors, string and cons, we introduce common type that can be used in as state. We provide update actions such as insert, delete, modify, and nop. These actions target state or type value. We also define the function applied it. Beagle core functions are implemented as a constructor of the date type Beagle and their interpreter. We implemented as a data type BeagleD, which is update based and operates on date type value. And Beagle returns the result state and transform trace information. So we define the update based version Beagle Delta. The properties that must be satisfied when converting state based to update based. Semantical equivalence. equivalence for get, the two results are the same even if root differs. Equivalence for put, same result. Next, there are well-behavedness conditions, put idle and put get. However, if the state-based is well-behaved and the update-based is semantically equivalent to state-based, then these conditions are satisfied. These proofs are straightforward. Therefore, in this study, we incrementalize Beagle with a focus on satisfying semantically equivalence. As an example of update base, we'll introduce skip. In the state base, skip is a core function that skips change on the view side. So in the update base, its behavior differs depending on the update actions on the view side. For NOP or modify that result in no actual change. When applied, it returns NOP. For insert or delete, which always bring about change, the transformation fails. Next, evaluation. We use a family to family name model based on family to person. We modify the size of the source, number of families. For both get and put, we measured the processing time for insert, delete, and modify. Here are the result of the measurements. The upper shows the result for insert. And the result for delete is similar to inserts. The lower shows the result for modify. In the state base, the time increases as the number of families grows. In contrast, in the update base, the time is shorter for all update actions and no change depending on the date size, expect, modify, put, modify. The reason is the use of skip put requires access to the source state. A conclusion is as shown. As future work, introducing the val type causes the possibility of runtime type error. To solve this, we plan to investigate update container. Thank you for your attention.
Questions?
So maybe I missed the point, but also, have you completely defined the semantics of your language and prove the properties or not? In your slides, some slides, you said this property, that property. Have you already proved them?
Yeah. One more, please.
Well, have you defined the semantics of your language, and have you already proved the properties?
prove. The
No, so the next one, I think.
these
Oh yeah,
are
this is semantics, and also the next one, next slide.
next slide.
No. Where's the previous? Yes, yes. Have you already proved?
Yes.
Okay.
Sorry, but the these proofs. Not on this slide. So.
Could you say again?
The proofs, not on the slide, but the semantical equivalence for each core functions are proved.
So your proof has already been done.
Yes.
Oh, okay, that is good. Yes. And because in the abstract, I think where you said that this is ongoing work and you will prove or something like that, but you have already done it.
Yes.
Okay.
Thank you.
I have a question. I don't fully understand what you mean by incrementalized. Is it just about having operations or edits in the system so that you can skip certain changes?
I know now implementation and position based. So
position based.
ID is list or ID of list. So can't change. Sources ID and views ID is same.
Can you show us in the example? I think you have one slide, right? Okay. So in what way? So this modify then is what you mean by incrementalization.
Yes.
Am I right? Okay. So basically you do no op when there's no modification.
Sorry, one more please.
You do no op.
You do
when there's no modification. That's what you mean by incrementalization. It's okay. We can take it offline. Any more questions?
Thank you for question. Thank you for your question. So maybe I transfer what you asked. So, what is the incrementalization in your framework, right? So, he's asked about the no operation, but it is So it is just if the modify or change from old value to new value, which may which accidentally equal, then it is equal to no operation. That is an op. Yeah. So incrementalization is just instead of processing entire state, processing the operation sending from view to source and source to view. That's the incrementalization in our framework.
So that is not really shown in this example, right?
So it is the incrementalized part of the semantics. So we have to use both the state-based and the operation, and then the incrementalized version. The first one is the original one, and the second one is skip. This is the left side is skip, and the right side is skip D. So that D version is the incrementalized version. Yeah.
Right. Yeah. Let's thank Nasaki again. Right. Okay. We're coming to the last talk of this morning. It is a talk proposal, and is on the application of partial evaluation as a primitive for a modern network troubleshooting. So it's given by Ando Wang from Temple University in the United States.
Oh, can we start? Do you hear me? Okay, cool. Great. So in this talk proposal, as a network researcher, I want to share with you folks my thoughts on how partial evaluation might be generalized to greatly advance network troubleshooting. The insight is this. We all know, and you folks know better than me, partial evaluation can be used to compile a program by specializing an interpreter. The enabling technique here is PE identifies and removes whatever information available at the compile time. This is a very general process, and the question we ask is, can we use this as a general device to pre-process complexity in modern networks that are ever-growing in its size, semantics, and the concurrency and the failures it always had to deal with. Our initial progress is this. The PE formulation that we've seen previously in the previous slide that allowed PE to compile the program can be nicely adopted in networking. So here, the interpreter, instead of interpret a specific language, now provides the operational semantics of the network environment in general, given a certain concurrency and a failure model. And the target program is a network instance. We are interested in providing the specifics of this particular instance, such as the topology and the computation performed at each individual node. But the purpose in our formulation here is very different from the traditional PE that seeks to optimize the performance of a program. Here, we are interested in simplifying, generating a more tractable residual network that can be analyzed with legacy tool. By simplification, I mean to make the impact of concurrency and failure clear and explicit, to reduce the size of the network, and to remove certain semantics that might make troubleshooting hard. So that's the idea here, and if we can implement all of them, it's going to be very nice for networking already. But there's still a limitation, which is in the bottom you can see the root causes was given in the context of the residual network. It would be more interesting to provide that kind of feedback in terms of the original network, right? In terms of the original topology, event handler, decision logic, and also to provide feedback in the concrete concurrency or failure scenario. So to achieve this, the classic PE process seems to be inadequate, and we might need a generalization. We might need a reverse process, which we call PE reverse. So in the rest of this talk, I want to provide some evidence and also potential benefit, how this can help networking, addressing all three sources of complexity, right? Size, semantics, and concurrency and failure. So let's begin with semantics related to complexity first. We have the most developed idea here. So complexity related to semantics may be best illustrated in SDN, software-defined networking, which has been one of the biggest topics in the past 2 decades in networking that seeks to transition traditional distributed protocol into centralized software. And the 2 key motivations behind this is 1, to make innovation easier. Traditional distributed protocol was notoriously hard to evolve, right? The notorious ossified problem. And the second motive is to make things simpler because, again, right, networking, it has been notoriously hard to manage. It's very expensive. And so we want to make it simpler instead of making the admin operators master of complexities. And over the past 2 decades, right, not surprisingly, under this umbrella SDN, the technique, the enable technique is mostly language-based. So we've seen proliferation of new language DSLs coming up with new constructs, language supports that make innovation possible. And indeed, SDN did a great job in fostering innovation, but it's hard to say whether SDN actually simplify networking or not, right? Many people may even argue that with SDN, networking these days are even harder to troubleshoot. And from a language perspective, it's not surprising because many of these new language features they make innovation, but they also complicate debugging. So next, let me show you a concrete example based on our own research. Consider this requirement, a very simple requirement actually. So we would like to allow traffic from node 1, pass from 1 to 3, and reaching the destination 4. 1, 2, 3, 4. You can think of them as switches. The subtlety here is we want to make this happen. Only allow packets, right, satisfying 2 asset control, both echo 1 and echo 2, under certain failures. We need to consider failures that might occur in the first link between 1, 2, and also link 2, 3. So a naive approach, right, to deal with this is we add backup links here in the dashed line here, and we consider all possible failure scenarios. We have 4 failure scenarios in this case, and we can enumerate, right, all of them. It's possible, but obviously tedious, right? So to avoid this kind of enumeration, we introduced ForLog, which is an extension of daylog with conditions, right? I'm not going to into the detail here, but the gist is with conditions, we are now able to encode the link conditions within the network itself, so that a single program here captures, represents the network behavior under all possible failure scenario, and verify one single ForLog program allows us to verify the network under all possible failure cases. So that's great, but surprisingly or not, the ForLog program is harder to understand or debug compared to standard daylog, right? As illustrated in the 2 examples here, right? The top part is the correct configuration, and the bottom is a buggy configuration, right? It's actually not easy to see, even on this simple case, right? Why the placement of echo 2 in the second link 2, 3 might be a problem, because it's going to cause the bypassing of echo 2 only when the first link fails, or a seemingly irrelevant link. To help addressing these kind of tricky debugging due to this new ForLog feature, we have some implementation showing how PE can help. And this is by a classic use of partial evaluation to remove layers of semantics, right? So given a ForLog program and an interpreter, PE can be used to remove the ForLog conditions. And here I'm showing some fragments of our implementation. The top right is the ForLog encoded in Prolog. We do the encoding in Prolog because that's our implementation language, and instead of dealing with Prolog, doing this embedding makes the rest of the implementation cleaner and simpler. And top left is the ForLog interpreter. You can see it's a natural extension of standard Prolog meta interpreter to incorporate the handling of the Fourier conditions. And the middle left is the partial evaluator. We implemented it's very primitive, right? We hand-coded the unfolding, folding transformation. It's embarrassingly primitive, but it works. And the bottom left is the resulting residual program, and you can see how the residual program shows the features from both the interpreter and the Fourier program. And we then sent this residual program to debugger we also implemented, and top and bottom right is the debugging session, right? Showing you how we correctly identify the problematic configuration in terms of Prolog. Now, the remaining question is, identifying it in Prolog, that's nice, but can we directly identify the faulty line in Fourier? Can we actually develop a reverse process of partial evaluation? So in the review, we get very interesting feedback that reversing partial evaluation in general might be hard. What makes me optimistic about this in the context of troubleshooting is we are not dealing with a general reversing process, right? The important thing is it's more like mapping. It's more like establishing correspondence between the residual in the bottom and original Fourier program we already know, right? So that's what makes us thinking it's not entirely impossible. Okay, so far I hope that it shows you how feasible, right, partial evaluation might help network troubleshooting, but we are still using some pretty standard, familiar application of PE. Next, let me show you some hopefully unfamiliar use of PE, considering the site-related complexity, which is probably best described in terms of internet routing, right? One of the largest computer networks we have so far. And BGP, Border Gateway Protocol, that's the single de facto protocol that's running the global internet, computing internet-wide path. You can think of that as the language spoken by every IP router to establish this internet-wide path. BGP research was really hot from 2000 to, I think, around 2010. And at that time, network researchers everyone loved to hate BGP because BGP is a broken protocol that generates numerous papers attempts to fix it. And one of the problems, it's still not fixed today, about BGP is it as a distributed path computation protocol, it doesn't provide convergence guarantee. It can diverge. It can non-terminating, do oscillating computation all the time. And the reason is because unlike some other standard algorithm like Dijkstra that use some universally accepted criteria to select a path, BGP allows the participants, like an internet service provider, to set arbitrary path preferences. Provider can favor cheaper but longer paths, right? That's causing this divergence problem. And determining convergence for a specific BGP instance turned out to be NP hardware, not surprisingly. And that makes the size of the internet really matters in this decision problem. And in the moment in networking, the way we address these scalability challenge is by reducing the network size before analysis and to compress the network size. Popular methods rely on heuristics that often exploit certain property of the network, such as symmetry in the topology. And in contrast, we think that partial evaluation might provide a far more general method to compress network. And the idea is if we have a BGP interpreter, essentially you can think of that specify the BGP protocol itself, and a BGP instance, its topology, and some partial information about the routing policy. By partial information in the top right here, you can see we mean all available paths, right, towards certain destination. For example, here you can see all the available paths towards destination 0. But we don't know the path preferences. We don't know how each node, right, each node preference among these candidates towards destination 0. And the opportunity here is we think that PE, by performing path computation in the BGP system that do not rely on path preferences, we have good reason to believe that PE should be able to identify nodes like X and Y that doesn't really depend on path preference because they only have a single path, right, to the destination. And by identifying them, right, we might be able to use PE to drop them, to eliminate them, and producing a residual smaller network, something like showing on bottom left here. So if we can get that, and suppose we also get supply additional path preference information, then we can leverage traditional technique, right, to actually analyze and identify the problem, the so-called unsatisfiable core, right, and minimal set of routers that actually causing the oscillation. Right. In this case, the intuition is regarding destination 0, node 1 and 2, they are preferring each other to get to the destination. Right. So there is some cyclic preference here that's causing the divergence. Okay, that's, if we can do all of this, that's nice. It's going to be a very general technique, right, to address, identify, detecting oscillation. But still, right, the recurring challenge here is, can we map the identified minimal call, right, in the residual network back to the original BGP instance, right? How to do that? Okay. And finally, let me show you the last scenario we identified. Hopefully, maybe the most unfamiliar case, right, and also the least developed idea here, using PE to address complexity related to concurrency and failure. So concurrency and failure, right, it has been a problem for networking since its birth, right? But in the emergent paradigm called INC, in network computation, the problem is severe because traditionally we have well understood techniques to address those distributed system complexity, message loss, reordering, etc. Right? We have this standard technique, timer retransmission. The problem with these techniques is they are expensive, and that's why these techniques are only employed in the end host, right, in TCP for them, not in the switches or routers with limited resources. But with INC, we are designing protocol for switches and routers, and so these expensive techniques are not abandoned, but they are avoided. And we are seeing a wave of new lightweight protocol that the designers, these INC designers, they claim and believe the protocol correct, but it turns out to contain bugs. So we asked, can we use PE to facilitate, right, the INC design? The idea is to use an interpreter to model the concurrency and the failures the INC design is considering, and use PE to mix the concurrency failure model with an INC event handler to generate a holistic model that can be analyzed using, say, an existing model checker. And again, the result is to how to map it back to the origin to explain the problem in terms of what part of the event handler is causing problem in what concurrency and the failure scenario. So that's my talk, and I hope that I show you the potential feasibility and also challenges with generalizing partial evaluation to advance modern network troubleshooting. Yeah, so thank you. Ready to the
Thanks, Andrew. It's interesting to see PE be used in a different context. Any question or feedback for the speaker before heading out for lunch?
Thank you. Very, very interesting. So, in a scenario that people probably might consider more realistic than ever, you might have a router or a switch provider, okay, who will put in a mode where it is intentionally actually creating divergence, right? So helping create divergence in order maybe to take down the internet at some point. So is that, will your analyses in principle help? You probably have to know something about the internals of the individual switches, I guess. But will your analysis then maybe at scale help at identifying possible subnetworks or paths, routes that might be involved in a divergence attack?
In divergence attack.
Yeah, think of it as somebody not being interested in convergence, but actually in a divergence.
Okay.
There's lots of people are probably going to be interested in that.
I'm not sure.
Us here, I guess.
Okay. Okay, so Okay, let me try to rephrase your question. So I think there's a few issues involved here, right? One is what's needed for us to analyze the divergence, or whether we need access to the software, to the program. And that's actually an excellent question. So in general, here we assume we have access to the internals, but it's not always the case in network in general. But on the other hand, right, reverse engineering, that's lots of effort in networking, right? There's many techniques that do not rely on the internals. It can be a big research in itself, but in this early stage, we assume we do have access to the internals. Now, on the other hand, regarding divergence, if it's a networking problem, I'm not sure whether you really need to investigate in the router or switches to cause divergence. There's many other ways to cause divergence, right? So you talk about, I'm not sure if I understand your question clearly. So when you say calling divergence, the potential, can you elaborate on that?
Somebody attacking basically the internet at scale by providing, providing cheap switches or whatever that work normally or mostly until they're intended not to work anymore.
Can you elaborate on
work in
potential?
The sense of actually making it, diverge in this case.
In diverge, so there indeed, right? There are real incidents in history reported, and all of them was caused by misconfiguration, not intention, not malicious intention, by misconfiguration, and it bring down the internet for minutes and hours and minutes. That's big revenue loss.
Okay, let's thank the speaker again, and it is time for lunch.
of PEPM 2026. It's my pleasure to introduce our invited speaker, Nicolas Wu. Nicolas Wu is a professor of computer science at Imperial College London, where he leads the functional programming group. His research interests including algebraic effects, effect handlers, modular language design, and the use of functional programming techniques to structure and reason about complex systems. Right, Nick, the stage is yours.
Thank you very much. Okay, so a big disclaimer. There are a few disclaimers to make. One is that this is not the first time I've done this talk. So if you already went to the Haskell Symposium keynote a few years ago, when Ning Ning did the keynote as well, I gave basically basically the same talk as this, and she invited me to basically give it again. So here we go for part 2. So this is why we're just revisiting the evolution effects. And the second disclaimer is that this is largely a talk about history, and I'm wondering if we can turn down the speaker a bit. Is that possible? Because I feel like I'm going to explode if I carry on. Thank you, that's great. This is largely a history lesson, and the problem with history is that you can never get it right no matter how hard you try, because there's always something that you'll forget and you'll always have a biased view. And I'm definitely guilty of both of those things. So I'll do my best to try and be slightly objective, but I will certainly get all sorts of things wrong. And if you like to heckle, I don't mind you heckling during the audience, during the talk, and you can just tell me that I've got something wrong or tell me something I didn't know before. Certainly this talk has been improved a little bit since last time due to the heckling. Okay, so this talk is in 4 parts. I'm going to be talking about the history of evolution effects, starting with something like the history of programming languages, moving into monads, then effect handlers, and then higher order effects. Okay, so it's very peaked. And caveat, there's just too much history to cover everything. I'm not really going to make a good job of it. But let me just start with some basics. There's this common divide between functional programming and imperative programming, and it's been here for a very long time. It's been here essentially since the beginning. We've got Alonzo Church sitting in the functional camp, teaching us all about the lambda calculus. And then we've got his what became PhD student, Alan Turing, thinking about imperative programming. And so you've got, you know, the good guys versus the bad guys from the beginning. He's saying, you know, the right way to do programming is to use lambda abstractions. This is how we should understand programming languages. Whereas Turing says, no, no, it's machines and it's all about assignments. So this is how we should be thinking about what computation is. Fine. So this is where this story starts. So let's think about programming languages and maybe where they came from. So this is a history lesson after all. I'm at Imperial College London, so I feel like I have to start in London. In London in 1666. London is on fire. It's the Great Fire of London, started by some small bakery in some obscure alleyway, which basically took over the entire country. But 1666 is important for another reason. It's also the year when Leibniz completed his dissertation, The Art of Combinatorics. And so this is a snapshot of his actual thesis. And it's an interesting piece of work. It includes all sorts of stuff, including a proof of the existence of God from some hypothesis about and axioms about motion. It's an alphabet of human thought that he wants to build, the Alphabetum Cogitunium Humanium. My pronunciation's wrong. And the idea is that he thinks that all human concepts can be put together into some kind of common language so that we could start reasoning about things, so that when we're arguing about something, we can, rather than just arguing with random words, we can maybe write them down and then start calculating our way through an argument to see who's right. So that's kind of his goal. And so he also has some interesting writings. He says something like, when trying to get from England to Holland, I was detained for some time in the Thames by adverse winds. During that time, knowing not what to do and having nobody in the ship except sailors, I meditated on things and especially thought about my old design of a rational language. Just think about that scene. So he's on the Thames with nothing but sailors, and so he starts thinking, right? And so if we can have such, as I imagine, we could reason about metaphysics and morality just like we do about geometry and analysis. So he's really thinking about logic as a language. And he's writing this to someone called Galois, but not the one you're thinking of. So was he a programming language designer is the question. Was he thinking about disassembling and composing languages from smaller parts? Let's fast forward a little bit to a different keynote talk, but this one to a much more prestigious venue, sorry, PEPM, the Congress of German Scientists and Physicians in 1872. Emile Dubois-Reymond says, Basically, at the end of a long talk, which was about how there are limitations to what science can know, and that there are certain big questions that we'll never get around to answering, he says, ignoramus et ignoramibus. We do not know, and we shall not know the answers to these questions. So there are just simple limitations, and tough luck scientists, but we'll be out of a job if we try to answer everything. Fine. And that really annoys David Hilbert. David Hilbert, a few years later at the same conference, also a keynote speaker, responds to this message saying, wir müssen wissen, wir werden wissen. We must know, we shall know. So he's kind of very defiant about this. And so he decides that, okay, actually, I think we can decide with certainty the true answers to all scientific questions, or at least all mathematical questions. And so he devises in 1928 with Ackermann a whole bunch of interesting questions, but in part, one of the questions that he has is the Entscheidungsproblem, the decision problem, basically asking us, given a particular input statement in first order predicate calculus, is there an algorithm that answers either yes or no if the statement is provable? And it seems perfectly reasonable, right? Because we're thinking of a mathematical language. We know that mathematics is supposed to hold something to do with the truth, and presumably we can always calculate what the truth is, right? That's kind of the goal, the question. And I think at the time it was basically understood that the answer to this would be yes, right? People thought there's no question that mathematics can't resolve all of its own questions. But I think everyone in this room probably knows how this goes. But partly we've got Gödel in 1931 saying that any reasonable system of logic has true statements that cannot be proven within that statement. So that's already quite a worrying fact. And so we can always think about maybe extending the logic to have more predicates or something like this, or doing some more meta logic. But eventually we'll run out of meta, and we'll know that we can't prove everything within our language. Fine. And if it holds true, then perhaps, but maybe there is an algorithm that can prove that statements are one or the other at least. In 36, we get two answers to that question, again by Church and Turing, and they basically say no, there's no such possible answer. So we have the halting problem getting in the way. There are true limitations to what we can logically get to. Okay, and to this PL community, I think you probably roughly know where that goes. Of course, Turing was involved shortly after in the development of the first computer, and partly with the help of von Neumann and a whole bunch of other people. And I think the history here is quite difficult to get right and murky, so I will make no attempt to get it right, and I'll just go for something that's wrong. There was the EDVAC computer in 1949. There's also the ENISAC, or the EDSAC, sorry. And I think the Americans and the British fight over who got there first, but it was definitely the British. And so there we have it. We have machines have made their way into our world that can compute. And of course, the first thing that happens is that we start thinking about a programming language for these machines. So rather than working on, literal punch cards like this, we want, well, actually, this is a punch card that is exactly this code. But rather than just working with wires, we want to work in a programming language where punch cards like this translate exactly to things like this, right? So we think we've got it hard working in the terminal when we're not using VS Code, perhaps. Imagine if you really had, a hard limit of 80 characters set by a piece of paper, and that you really have to sort of punch in the exact symbols that correspond here. So the way to read these is literally, this is a single line of code. And so you've got, here is each of the columns that correspond to where the character is, and going down the page is going to be the bit sequence that you require to make that particular bit character for that particular line. So a stack of punch cards, each punch card is one line, a stack just corresponds to your program, et cetera, et cetera. So there are some people, when I give this talk, they're like, oh yeah, I remember punch cards, and I've got a few right here. But for most of us in this room, this is a forgotten thing. We have no idea where we've come from. Okay. But what did Backus say about this? He invented the language called Fortran, and he said in this really nice article in Think, which is one of IBM's notices, he said, much of my work has come from being lazy. I didn't like writing programs, and so when I was working on the IBM 701, writing programs for computing missile trajectories, I started work on a programming system to make it easier to write programs. Most people think Fortran's main contribution was to enable the programmer to write programs in algebraic formulas instead of machine language, but it isn't. What Fortran did primarily was to mechanize the organization of loops. So back from the beginning, it's actually interesting that it's control flow that's the thing that was difficult, or control flow was the thing that was in his mind in terms of trying to come up with a programming language. And that'll become, obviously, relevant in a talk about effects. Fast forward just a tiny bit, or sort of in a round era actually, we've got Lisp, so a second contender for being the first proper programming language. And so this is McCarthy taking a very different take on what a programming language should do, where we saw Backus in the previous slide thinking more about how we can work with the machine and talk about machine language and make that process easier. McCarthy's coming from the other perspective. What can we do with the lambda calculus and how can we enact that in a machine? And so these are the two views that we got right from the beginning, the imperative versus the functional, kind of attacking the same problem all over again. And we can see here that he really is writing the lambda calculus in his papers in 58. He's saying things like, okay, here's what a conditional expression should look like. We should handle each of the, in a case expression, we should handle each of the cases with saying if P is true, then if P1 is true, then do E1 and so on and so on. So this is starting to look something like we'd have in effect systems today even. He basically wants to say something like we should really have continuation. So continuation, if the thing is false, we should do something. If the continuation is true, we should do something else. So he's thinking about things in terms of continuation style, which will become relevant later along. Another thing that he has in this really early paper is the map function, which as functional programmers is one of the first things that we learn. So if you have some list X and some function F, then if the list is nil, then you do the nil thing, and if it's otherwise, you do the cons thing, you put them together, and so on. Interesting note is that I think car and cudder are the names of head and tail, respectively. So I find it quite amusing that they call it car and cudder in the underlying documents rather than what we might call head and tail, in the sense that what on earth does car and cudder even mean is probably the first question some of you are asking. And so one is the address part of a word and the other is the decrement part of a word. And obviously they correspond to the head and tail of a list, right? And I think the perspective here is that they're really thinking about what's going on in the machine. And even in this paper, which talks about lambda abstractions, they can't get away from the underlying concrete representation of certain data structures. And they're not fully making that step to thinking about things in terms of those data structures themselves. And I think that's quite curious as well. So, right. And also in 62, McCarthy comes up, as far as I can tell, with the first use of the word abstract syntax. So that's where we should go to understand this idea of having abstraction. So nice that he might have moved away from car and cudder, I'm not sure. Let's fast forward just a tiny bit further into Algol 58, where a number of people who established a lot of PL as we know it today, came together and decided to write a common language that they could use for writing papers in, basically. I think they were tired of reading papers about programming languages in all sorts of different languages, and they thought, I know, let's come up with a language that we can use to communicate in the CACM. Obviously, we didn't listen to that at all. If you look now in POPL', you'll see we never write, I think probably almost no two papers write in the same language. But what they did do is they laid a foundation for what kind of programming languages features we might like. And so it's nice to see that Backus and McCarthy, these two sort of fathers of the first imperative language and the first functional language, came together and created this thing, right? What was special about Algol? Well, it had things like iteration and also recursion. It had this idea of distinct assignment versus equality, so that we can actually tell the difference between these things. There was the idea of code blocks, and lexical scope was new to this language. Nested procedures and procedure passing was important too. BNF was invented, so Peter Noir and Backus was the other author of that. They invented what we now use to express our grammars in. And the distinction between call by value and call by name was invented for this language. So all sorts of interesting things came out of the development of this important language that's really seminal to us all. And Tony Hoare at the time said, it's a language that's so far ahead of its time that it was not only an improvement on its predecessors, but also on nearly all its successors. And if you look at the state of some programming languages today, then you might agree with him. Right. Let's move on a little bit into 1965. So I think the conclusion that I have is the first iteration of Algol feels exceptionally imperative in nature. And Peter Landin, I think, takes slight issue with this and starts thinking about whether or not it's possible to think of Algol in this sort of functional way. And actually, he's doing this because he wants to give a semantics to algol and understand that from a computational perspective, from a lambda perspective. And so he writes this paper in '64, The Mechanical Evaluation of Expressions, where he shows how you can translate some algol code into the corresponding, what he calls applicative expressions, which are just expressions that you can apply to each other. So literally just lambda abstraction and lambda application are the tools that we have. And some distinctions between lets and wheres, but it's interesting from a Haskell perspective, we're always allowing both lets and wheres in our languages. And he invents what we call the SECD machine, which is the first abstract machine for evaluating lambda expressions. So he shows us the connection between Church's calculus and machines themselves. So the SECD machine allows you to actually take a lambda expression and fully evaluate it right the way down. And so we see this really clean connection between the two in this paper. And so I think this makes its way into the sort of the standard understanding of algol in '65, and he shows that basically the two languages are the same with all the different concepts corresponding quite naturally. A little bit later on, Landon gets a little bit more extreme with his views and decides that what we need is a new programming language called ISWIM, which means if you see what I mean. And I think it was the fashion at the time to name languages after obscure acronyms, and I think he was making fun of that. So in 1966, he writes this famous paper, which I think I'd recommend to everybody in this room to read, just because it's quite fun to see how research has changed over the years. This was definitely a seminal paper, but when you read it, you see that it's just written in a completely different, much more flourished style than we would today. And in this paper, he basically thinks about doing church without lambda is the subtitle that he gives to this paper. So he's thinking, okay, so the lambda calculus was a really nice language to give the semantics of things, and we were able to give the semantics of algol using that. Great. But what if we were to start from the ground up and think of a language where we're not writing lambdas, but we can program in that style? And so he's thinking about basically what I would say is a real predecessor to Haskell. If you start looking at ISWIM, you'll see huge similarities between that and the way Haskell ended up being, and that's no coincidence. So he wants us to be able to write programs like this and where you have some kind of expression with a where clause, just sort of saying how things are and plugging it all in. What's interesting about papers in these days isn't just that the content of the paper is written and expressed in a different way than we would today. They also have something fascinating, which is at the end of the published paper, you get a transcript of the questions that were asked at the talk. And so you can see who asked what and how it was responded to. And I think that's really, again, an insight that we no longer have. And so Peter Noir says, oh, well, regarding indentation, since ISWIM was an indentation-sensitive language, in many ways I'm in sympathy with this, but you would regret it because of the kind of rearrangement of manuscripts done in printing, which tickles me because, as you all know, when we're using LaTeX and we're trying to get that camera-ready version with just the right number of pages, it's an absolute pain whether it's indentation-sensitive or not, right? But yeah, so these problems have not changed over the years. So this is a language like Haskell that has pattern matching, it has where clauses, it has garbage collection, and it's indentation sensitive, but it's also equipped with equivalences for reasoning. So he wants us to be able to write in our programs equivalences between expressions and hope that your language will be able to resolve those equivalences and say that these two terms must be equal under this in this language. So for instance, he thinks that the languages should always have these rules, so sub-expressions should be congruent. We should have multiple ways of defining the same constructs, so let statements and where statements shouldn't be so different. He thinks that we should have built-in expressions, so true and false resolving as an if then else statement should be doing something like this. And also, and interestingly for us, he wants there to be user-definable DSLs, so domain-specific languages that the user can write, and then use those languages in the code that they're writing itself. And within those languages, you would be able to write some equalities on the expressions that are there as well. And so that's what we have here. So he says the problem orientation of ISWIM can be characterized by additional axioms. So he's thinking about additional equalities between operations here. In the simplest case, such an axiom is an ISWIM definition. The resulting modification is called a definitional extension of an original system. Okay, and when I said the language in these papers is a bit hard for us to decipher today, it's basically stuff like this right the way through, right? So you have to really read it quite carefully and get into their mind and work out what's happening. Okay. I want to kind of move on a little bit to the idea of structured programming, because that was really relevant to ISWIM. ISWIM was really good for reasoning and doing structured programming, and I think that's probably one of the biggest gifts that it gave us. And structured programming was, let's say, advertised by Burstall in '68, where he's viewing the idea that we should have code and where reasoning about that code should follow the structure of that code. So he's tying together the idea of data structure and induction should really be tied in together. And so to prove the correctness of your favorite algorithm means to follow the structure of that algorithm to make equalities about that and to make statements about that. So he implements really early versions in '68 of the concat, and this is the fold right function, which collapses a list. And then he writes about a function for sorting via flattening trees. And so if you look at this code, you'll see it looks fairly functional. It looks like Haskell again, but this is an ISWIM, of course. And what's interesting about it isn't so much that he has an algorithm that does tree flattening. It's that he actually does a proof of its correctness by induction over the structure of that tree as well. So we're seeing all sorts of nice techniques that we'd like to mechanize today, but implemented by hand at that time in a language that didn't ever really exist at the time. So there was no implementation of ISWIM in this period. That came much, much later. It was really a pen and paper language in this moment. Okay, and the idea of this really takes off and then was popularized by others. So Dijkstra, Hoare, and Dahl wrote this really nice paper called Structured Programming, where it goes through lots of examples of why you might want to structure your code rather than just using a control structure. You can actually use data structure to manipulate things. And again, that's something we would teach all our undergraduates today. And Hall writes that there are certain close analogies between the methods used for structuring data and the methods for structuring a program which processes that data. So again, these ideas of making program and data be the same kind of thing is emerging at this stage. But we're not quite done yet, because another big idea that came out in this Next 700 Programming Languages paper was, I think, the foundations of denotational programming, or denotational semantics. So he says something like, the thing an expression denotes its value depends only on the values of its sub-expressions, not on other properties of them. So that's in '66, and in '71 we get Scott and Strachey showing us how to unpack this into mathematical formulas. So we've got an expression, and we give that a denotational semantics when the meaning of the expression comes about as the meaning of its parts. So we've got this V here, and we're looking at the parts to combine them. So that paper was really foundational in the sense that it gave us this idea of having what I might start considering a higher order language with interesting pattern matching, with lambdas at the heart of it, and yet that should be quite easy to use, that's ready for structural induction, and also giving us denotational semantics. So it's an important paper for lots of good reasons. Okay, so back to our initial slide, we've got functional versus imperative. Are they really at war? Well, Peter Landon, I think his take would have been slightly different. He would have said, actually, there are all sorts of different words that we might use to describe what we want. Maybe we're saying things like procedural, non-procedural, algorithmic, heuristic, imperative, declarative, functional, descriptive. But we probably should have a different classification of the kinds of languages that we want. So here's a new word that he wanted to invent to describe the good languages. And he thinks that we should call them denotative. So the denotative languages are the kind of that part of the imperative world, that part of the functional world that we think is sensible, right? Okay, so maybe we've got some kind of, mystical, right? Perhaps there's a means of working with pure functions and side effects in synergy. And this would require a denotative means of expressing side effects that supports reasoning. So we should put denotation at the heart of our languages. We should try to understand what the code means. And if we can do that, then maybe it doesn't really matter too much whether we're doing imperative or functional programming. Okay. So now on to monads. We all perhaps have heard the folklore that monads are burritos. If you haven't, well, welcome to the world of monads. Monads or burritos was a kind of a joke, I think, that Brent Yorgi wrote in a blog post where he was just talking about the monad tutorial fallacy. This was a kind of interesting time on the internet when if somebody learned a new idea, then they would write about it in their blog. And so there were lots and lots of different analogies about monads and what they really were. And so to kind of talk about this aspect, Brent jokingly wrote, monads are like burritos, and then I think it took off a bit too well. So that's where that idea comes from. But because we're doing history, I thought I would take us right the way back. So this is South Africa in 71,000 BC. And I kid you not, this is actually a picture of a rock that exists from 71,000 BC, we believe. And archaeologists had to look at this thing very carefully. You can see these ochre red lines on it. And they've gone so far actually as to write papers about this. So it's an abstract drawing from 73,000-year-old levels in this particular cave. And they've analyzed this rock very, very carefully. And you can see these red lines where the markings of somebody has, they've very carefully written something here. And the question is, what is the message that they're trying to get across? Now, to me, it's absolutely obvious. You look at this and you realize that mankind's been striving for Haskell for a very long time. Okay, so that's not actually the history of Haskell. The history of Haskell was kind of spotted nicely in this paper, not in South Africa, 71,000 BC. And so here's a nice picture with the people who got together and wrote the first Haskell report. And you can read all about this in this nice report. I would recommend you read that too. And I think their take is that Haskell brought lots of different things. One of the important features that it brought was the class system. But another feature that it did bring, I suppose, was monads. I say I suppose because it wasn't in the original design of Haskell. Monads came not as an afterthought, but as a kind of a solution to a problem, which is how do we deal with I/O? And the initial versions of dealing with I/O were really just about having a single pure function that took in a string and output a string, and the input string was lazy, and you could produce your output and then keep on consuming some more of the input as you go to react to the world. And then, of course, monads became the solution that they fell on and was shipped in the first version. So I thought it'd be good to just go into the history of monads a little bit and see where that came from. So if you end up being interested in category theory, then one of the rituals that you'll probably go through is picking up a copy of categories for the working mathematician and probably being a bit confused by what's in there. But it is a good place to look at where things came from. And right near the beginning, MacLean says that, monads came as a construction in passing in another paper that he wrote. Here it is written in 1956. And it's fitting that it's in French because that's what he wrote in this language. And here it is saying something about the utilization of two categories, K and L with a functor T, et cetera, But these four lines are what he's referring to in his book, saying this is where monads were first introduced in passing, right? That's what he thinks a monad is in this place. So Godeman does a slightly more, a slightly bigger exposition of this, again in French, where he talked about monads, and it started to become a bit more clear. In the paper, you can think of K as being return, P as being join, and you've got an equation here at least that looks like the monad laws, if you know what they are. But basically, this is the first time when we really start seeing monads crystallizing in the way we would understand them today. And so for years, these things didn't really have a name. And I don't know if that's actually better or worse than today, because if you tell an undergraduate that we're going to learn about monads, suddenly they look terrified. And if you tell them we're going to learn about stuff, it's OK. So they called it the standard construction, or the fundamental construction, or just triples. But what about the word monad? Where did that come from? Why do we have it? So that was due to someone called Jean Benabou in '67, and he's writing about bicategories. And he wants to play on the word monoid, but actually he's not thinking about that so much. He's also thinking about monads as opposed to polyads. So our choice of monad comes from an example of definition 5.5. 5.5 is about polyads, and from polyads he basically thinks about not multiple arguments in these things, but one argument in these things. So it's a monad rather than a polyad. So that's the idea, really. So it's not so much about monoid, although it does bring that in. It's in contrast to polyads, which is not a concept that we use so much now. Okay, so that's where monads came from, and I think understanding where category theory injected itself into computer science started out. So as far as I can tell, the categorical semantics were basically explored by IBM as a kind of an initial idea. We've got Eilenberg and Wright writing this paper about automata in general algebra. They're talking about universal algebras for and for automata using Louvre theories. For those of you who know about effect systems, Louvre theories are a way of talking about operations and equations between those operations. And so it's really nice that in one of the first uses of computer science with category theory, we have something that harks right to what we'd think of now. Let's see. It's interesting as well that in this paper, for them, it's saying basically this paper contains nothing new except perhaps for a new point of view. I think that's such a throwaway remark that you know, having new perspectives on old material actually is super useful, and we've seen that time and again. So I don't think I would phrase it quite like this. I think it was actually a really important thing that they did. In '71, Algot started talking about algebraic theories for program schemes and wrote about monadic computation and iterative algebraic theories. So that was in '73. So he's thinking about iteration, thinking about how that can be done. And he's connecting Louvre theories with the way we'd study Turing machines. So that's where we have some interesting work to start with. Rewind a little bit to 1970, so just about 3 years or so before, we have Mac Lane, and he was suggesting to Gauguin that maybe he should apply for a research fellowship at IBM. And so, you know, you've got the founder of category theory saying, why don't you apply this stuff in IBM? That would be a good idea. And so Joseph Gauguin goes ahead and forms what was known as the ADJ group, or the adjunction group, or which they were trying to do something like the Nicolas Bourbaki program, which was a rewrite of not foundational mathematics in the Bourbaki style, but rather the foundations of category theory the foundations of computer science using category theory. So he and Thatcher, Wagner and Wright get together, and they write this paper called A Junction Between Computer Science and Category Theory, Part 1. And I think they had something like 4 parts planned out where they would go through all these different constructions and show why category theory is the foundation of computer science. The joke here is that an adjunction is a categorical construction that's quite important, and so they're writing a junction between and I. Okay, so they like the puns from the beginning, and that's why they call themselves the ADJ group, because they're the adjunction group. Okay, so then there was part 2 of this, which shows some more examples of these ideas, but it was a hugely successful project, although in the end I think they didn't have time for any more of the parts. They only got as far as part 2 and then ended. But they did talk about things like initial algebra semantics and continuous algebras. Initial algebra semantics is the way that we would give a semantics to things like a fold over a list or a fold over some larger data structure. It's the way that we would give proofs in a language like Rock or Agda. It's all about an initial algebra semantics insofar as induction is concerned. But yeah, they never made it past report 1 and 2. And I forget why this slide is here. So we've got an algebraic theory of recursive programs. Okay, so they use, that's right, so Birstall and Thatcher used monads to explain stateful programming and how it was related. And so they have this diagram here where you've got the familiar semicolon in the middle, and they're saying, okay, we should be using monads to think about stateful programming. So this is in '75, quite a long time before we think of monads and stateful stuff today. So what about monads and the lambda calculus? Where did those connections come in? So we've got Dana Scott, who thought about denotational semantics, and he writes this paper in 1980 relating theories of the lambda calculus, and something he says is that we want a pure theory of functions, and that is category theory. So he says, everyone agrees that the lambda calculus is a theory of functions, but we must ask what kind of a theory? And also, have we got the best theory? Personally, I think we should also inquire, how does it relate to other theories? I certainly find many discussions far too silent on this last issue. And then he goes on to say, what then is a pure theory of functions? The answer, category theory. So he thinks that if you're thinking about functions, then you really should be thinking about the foundations of that, and category theory is the right lens to view those. Fine. In 1980, we have Eugenio Moggi, and he takes this view and uses monads to give a semantics of computations. And so this is the 88 paper where he explicitly thinks about the lambda calculus of monads. He takes the categorical semantics and he shows various monads and why they're relevant to programming. Right, so he thinks about side effects and state, side effects with state and exceptions in monads. And he makes that crystal clear in 91. There he models other notions of computation. So we've got partiality, non-determinism, side effects, exceptions, continuations, input and output. All of these different examples were made in that paper. So the story for effects is obviously related to that, but in the way we'd understand it today, I'd like to take us back to 85 when Phil Wadler is thinking about how we can replace failure with a list of successes. So how can we record for a program to fail? And he's thinking about lists and laziness and combining these ideas together. And so he's thinking about exception handling, but in a kind of a listy way. So that's what he does in 85. And when I read this paper, I was quite excited because I'm at Imperial College London ICL, and he says, part of this research was performed while on research fellowship supported by ICL. Like, wow, Imperial were at the heart of this stuff as well. That's really interesting. And then I saw Phil at, I think, ICFP, and I said, Phil, I didn't know that you were at Imperial. And he said, I didn't know either. Because ICL, of course, doesn't stand for Imperial College London. It's some completely other company, a different company, so there we go. It does not mean Imperial, it's something else. Okay. In 1990, although it was first submitted in 88, Spivey looked at the functional theory of exceptions. So at the time in 85, Phil Wadler was thinking about exceptions, thoughts about them in terms of lists. Spivey also took a look at this, and I chatted to him about this, and I said, had you read Phil's paper? He said he hadn't. What he was doing at the time was reading MacLane actual, and then when he was reading MacLane, he got to the monads, and he thought, huh, this is what we should be using for composing together exceptions. And so he introduces the word maybe, which we use today for programming with exceptions, and he explicitly uses just and nothing and shows how we can do that. He uses return join and the fish operation, which is another way of doing composition, and talks about these things explicitly. So he's very much thinking about monads and programming with monads in the way that we do today. So this is, I think there's almost no difference between what he's writing and how Haskellers are taught to write with monads in that particular paper. Alongside all of this, you've got Richard Bird, who's thinking about the theory of lists. And so he's thinking about how can we do program calculation, program derivation from a specification? How can we reason with equations? And what do we do with this? So he works on laws and properties of programs, and he plays with those and works with those to go to actual implementations. And he writes something like this, which is a way of doing a map f over a list x plus y's. And he looks at the different properties that these have. And Spivey comes along 2 years later, sees this paper and says, hang on a minute, there are also connections to category theory here as well. So he says, well, we should really be thinking about categories not just for programming with exceptions, but also programming with lists. It's all the same stuff, the same monads apply. And so let's see, I think he says something interesting here. Many of the laws in Bird's theory of lists are precisely the conditions for various constructions to be functors, natural transformations, adjunctions, and so on. He basically says in his future work that he should be thinking about the theory of monads seems especially promising in this connection as Beck's theorem on classification of algebras, yada, yada. So he's basically saying monads are the way to not just think about exceptions, but also about non-determinism and all sorts of other things. He also implements a variation of what we'd call the free monad today, which is basically a way of turning syntax trees into a monad where binding an operation is syntax substitution. And so we see that this is where the bind symbol comes out in the programming context for the first time, at least its type does. Its name is subst in that paper, so subst is bind. That's not how monads made their way into mainstream Haskell, though. So although this theory was well established by Spivey, I don't think it was popularized, and I don't think people knew about it particularly. But Wadler did find this paper and did pick it up and realized its value. And so in 1990, he wrote this paper, Comprehending Monads, where he added the idea of monad comprehensions. So you can write some things that look like set comprehension notation, but we're talking about monads. And he, in 92, does the essence of functional programming. He has an invited talk where he talks about how we should be using monads for functional programming. And the great thing about this talk is that he has all sorts of different variations of monads and explicitly shows how each of these are useful for programming. So we've got interpretation, just as usual, the identity monad, and we've got error messages, got state, output, non-determinism, and I think this is the TARDIS monad for those of you who like strange computations that work forwards and backwards. Now, that's not quite the end of the story, because one of the troubles with monads is that they don't compose very well. And so that means that whilst you can use a monad to describe a particular effect, if you want your effect, if you want to have more than
Alex talking about effect handlers for modular search.
Hi everyone, I'm Alex, and this is some work I did in collaboration with Tom Shrivers. The title is Staging Effect Handlers for Modular Search. As you'll see soon enough, this is a project about constraint programming. There you go. So for people in my generation in the audience, which I think haven't joined yet because they're still late, this is sort of, you know, Instagram reel addled version, sort of no attention span version of the talk. I think constraint programming is quite cool. I think it's not talked about enough in sort of wider circles. And so what we did is we came up with a new way to implement constraint programming in a functional setting using effect handlers and algebraic effects. And what it turns out to be is also a very sort of low-hanging fruit application case for multi-stage programming, where with just an extremely naive, extremely simple implementation, you get quite impressive performance boosts in terms of runtime. So I need to sort of introduce constraint programming for people who are unfamiliar. So just a quick show of hands, who has heard of constraint programming? Okay, that's some people. It's good. So the basic gist of constraint programming is that we have some variables and we have some constraints on these variables, and we throw these constraints at the system, and the system just figures it all out and finds some solutions. So this is what a sort of Platonic ideal sample of a constraint program looks like. This is the famous n-queens problem, probably the most sort of textbook example of a constraint programming application, where you say that you have n queens, these are pieces on a chessboard, and they need to not be able to attack each other. And so each of them is on one row, and they can't sort of share a column, and they also can't share any diagonals. These predicates, these all different and no diagonals, each have their own sort of implementations, but they just throw these things at the system, and the system helpfully computes the solutions, which are the assignments of values to these variables that satisfy all the constraints in the system. So this is the first solution of 8 queens here, I think, which puts the first queen in the first spot, and then the second queen in the 5th spot on its row, and so on and so on. So what's going on behind the hood in these systems is that there's a model, which is the thing here on the left, and a constraint solver. The model is sort of the description of all these constraints and what needs to happen in the system, and this can contain branching. So here I just have a sort of silly little sample program where we can have non-determinism. We can say this branch must be true or this branch must be true. And then the solver itself is the thing that sort of does the magic. This keeps track of all the constraints and then sort of guides the process of finding values for them. Commonly, what they might do, for example, is they might keep a domain for each variable, which is sort of the set of values it could take. And then as you're adding constraints, they remove stuff from these domains to guide the search into finding valid solutions that satisfy all the constraints in the system. Now, constraint programming by itself is not sort of super a thing. It can quite rarely be done on its own, but usually we pair it up with some other paradigm, because what we want to do is we want to programmatically construct these constraint models because of well, a wide variety of reasons. And so what we end up doing often is we embed constraint programming in some other thing. Now, historically, in the ancient times of late last century, what happened was people paired this up with logic programming. They called it CLP, constraint logic programming. And now, more recently, we've been pairing it up with a whole bunch of things. Logic programming is still very relevant. There's also been a whole lot of push to integrate this with functional programming, but also with imperative stuff, with Java, OOP, and these are always some kind of DSL of some kind. But what we're focusing on is the functional way of doing constraint programming, which pairs quite nicely with a sort of combinator design for a library that we like in functional programming. And so this is that same program from earlier, just written in a slightly more realistic way in something like Haskell. What we do is we generate with this nQueens function, we generate the model, right? We generate this model with all of these combinators. You have that exist thing that makes n fresh variables for the positions of the queens, and you have all these constraints. You might also have something like this enumerate thing, which that's always the thing you have to do in constraint systems, or at least usually, which is that tells the system, hey, these are the variables that we actually want you to find the solutions for, because you might have some auxiliary variables, for example, and you don't sort of care for those necessarily as much as you do for the main ones that you want to output. So you create this model with a function, and then something else takes this model and evaluates it, meaning it gets that list of solutions. And so our approach, we call it effectful constraint programming. It's a variation on that theme of how to implement this kind of thing in a functional setting. So the core idea is this, and this is sort of the main thing, which is that the model itself that we produce, that's just an effectful computation. So that's just something that outputs, or that sort of contains a certain signature of effects. And then the solving bit, the thing that gets the solutions, is just an effect handler for this effectful computation. Now I need to sort of specify, when I say effects here, I don't mean effects as a first-class language feature like they do in, say, Coca. Those are great, I love them. What we're doing here is sort of effects as a library in Haskell using free monads and coproducts and folds and whatnot. Now, our approach is based quite heavily on an older paper written, co-authored by Tom Shivers, which is called Monadic Constraint Programming. And this is sort of right at a time when effect handlers were being investigated for the first time, so circa 2009. And they didn't know about effect handlers back then, and so they did something very similar, but instead of effects, they did it with just some monads. And there are some really good ideas that we inherit directly from monadic constraint programming. I think most important being that the constraint solver, so if you remember that component that sort of keeps track of all the domains of everything, that's a monad. That's sort of a state-like monad that you send messages to, and it does its own operations. And sort of in MCP, what they did was they carried it around, that monad, everywhere. That monad had to be everywhere to support sort of talking to the constraint solver at all times. Now, a good thing about doing it like in this way is that we can abstract over the solver itself. So we can have a system that's generic in the solver it accepts, just so long as the solver is a monad that has a certain number of operations, stuff like creating a new variable, adding a new constraint to a variable, some stuff to do with backtracking. But the cool part is that their system and our system as well are completely solver agnostic. So for example, I should probably say this. So for some examples of solvers that you might want, you can have stuff that are like work on integers, stuff that work on sets, things that work on graphs, and those are all separate things, but a system like this can handle them all the same. So this is what things looked like in 2009 when they did monadic constraint programming. The model was just a big data type that had a whole bunch of cases for every single operation you might want to have. So they had a constructor for adding a constraint, they had a constructor for making a new variable, they had a constructor for branching, for failure. And this is sort of annoying to extent, right? This means that every time you want to add a new thing to your system, to make some cool extension, you have to go back to this data type, add something new, and then change all your code to fit around this data type. So what we do instead in ECP is we do effects, right? So the first thing we did, rather than splitting off the model and the solver with that data type, what we do is we lift the constraint solver monad into an effect. Now this, I called it solvery for solver effect. Lots of libraries for effect handlers call this something like lift. It just lifts a monad into the sort of stack of effects you might have. This is just a very, very simple effect. It just takes that monad and suspends it inside a free monad. Because again, we're doing effect handlers in the style of the effectful computation is a free monad over a functor that is the sort of signature of operations you want. We have this sort of solver effect, and with these things you usually have some kind of smart constructor. Here we call it solve. What this sort of type constraint here means is that this solver effect needs to be part of the signature of this free monad. And what it does is it just lifts an operation from the monad into the effectful computation. So the model doesn't just need to do stuff with the solver, it also needs to do branching and failure. So when it meets a dead end, something, when for example, the constraint solver reaches some unsatisfiable state in the domains. For example, if a variable's domain becomes empty, that means, hey, there are no solutions to this thing. We add a non-determinism effect. This is a very standard stuff, just two constructors, one that can branch left to right and one that can say this is a dead end where we failed to find something, we need to backtrack. And it turns out this is all you need to do constraint programming. Just these two effects with a co-product between them are enough to write models for stuff like n-queens, which is sort of surprising because in monadic constraint programming they had all these constructors in that model type that don't have any direct correspondence to this thing, and yet we can express everything that they could with just these two effects. Again, everything here is solver agnostic, but for something like n-queens, we do something called FD. That's a finite domain integer solver, and that sort of works by representing variables as integers in some finite set of values. Instead of having that big model type, we can just have constructors for this sort of effectful computation type. So whereas before adding a constraint had a specific constructor in the model type, now this is just a function. This just takes a constraint and creates a fragment of effectful computation that sort of does the thing it's supposed to, which in this case is it accesses that constraint solver monad with that solve constructor there, tries to add the constraint itself in the solver, hears back from the solver whether that was successful or not, meaning whether the state of the system is still satisfiable. And if it is, then that's great. If it's not, then we fail, which triggers a backtrack in the system, looking for more solutions. And there's sort of a trade-off here because in monadic constraint programming, you had a separation between what these model actions are and what they do. But in practice, that was a bit of flexibility that was just unneeded because what you ended up doing always was just sort of this thing, for example, with constraints, right? With adding any constraint. And so we reduced a bit of flexibility in the system, but this makes the whole thing a bit easier to reason about because now you know that adding a constraint always has sort of this semantics, but you also never really need it to have anything else in practice. And so as we saw, the model in effectful constraint programming is an effectful computation. Now, getting their solutions is just an effect handler. So it's a handler for those two effects, for the solver thing and for non-determinism. But solving non-determinism, what that really means, well, how do you solve non-determinism? You search. So the basic algorithm is a search. Now, I won't really get into this unless you want me to get into this at the end, because there's some weirdness going on here in sort of the way I'm implementing this. But the gist of it is that this is a search procedure. You're searching through, so if you can think of the free monad as sort of generating a tree-like structure with those non-determinism left and right branches. And what you're doing is you're just doing like a depth first search or a breadth first search through this tree structure to find all the nodes, and that's where the solutions are. And sort of as you're going along, you're encountering like solver actions, like adding a new constraint, and you're sort of communicating that to the solver, and it talks back to you. And that's why it's slightly complicated in implementation, but that's sort of besides the point. Now, probably the best idea that they had back in 2009 when they did monadic constraint programming was these things called search transformers. And what they are is a way to build search as a first order citizen, to compose some building blocks into a bigger search algorithm that has the properties you desire. I think in the keynote, Nicholas mentioned this. Here are some sort of examples of transformers. One of them is depth-bounded search, and what it does is you give it a sort of height limit, and if you ever search below that, it just says, no, stop, don't go further than that, and makes you backtrack. Another one is node-bounded search, which keeps track of how many nodes you visited, and if you exceed a certain limit, it says, hey, stop, give up at this point. And these two are sort of very similar when you come to, for example, implement them, except for the way their state works. So transformers are inherently very, very stateful components. They have two pieces of state, because if you look at depth-bounded search, what does it need to do? Well, it needs to keep track of a node's depth, right, to know if it needs to prune it. A node's depth is what we call a local property of that tree, because it's sort of locally constructed. Whereas the node-bounded version, well, that's no longer local, because you can't predict the exact order in which your search algorithm will visit everything, because we allow for sort of arbitrary queuing strategies. And so that's no longer a property of the tree, but rather a property of the execution. And so that's a bit of global state. And so you have these two pieces of state that you need to wrangle around. We call them tree state for the local one, and eval state for the global one. And in general, transformers can use both. Here, these two, depth-bounded only uses tree state, node-bound only uses eval state, but in general, there are transformers that do need to use both. And so we have transformers in ECP as well, and we wanted to do them as effect handlers, because it's all about doing it with effects. And so the implementation needed to find a way to manage all that state, specifically the global state, in a way that's sort of nice and compositional. And so what we ended up with was we created a transformer effect. And the search procedure, what it does as it's sort of finding solutions, it has some places where it just creates these hooks. And these hooks allow the transformer to modify the behavior of the search procedure dynamically, right? And so what we end up with is a procedure that emits this transformer effect, but also handles the state of the transformer. So the search procedure is actually the one moving around all the state, making sure that that global state is in sync with execution. So this is what that, sort of mock-up of what that transformer effect looks like. It needs some parameters. It needs to know what type of tree state it should have, what type of evaluation state it should have, but also sort of the exact type of model we're working with, because it turns out one of the things these transformers can do is dynamically change the model we're looking at. And so that requires a bit of finesse. This sort of type for a transformer, a tree annotated with these transformer hooks, it looks a bit weird. It has this model sort of in a type signature, which looks a bit like higher order effects, but I promise you it's not. So even though it has sort of the telltale sign of higher order effect, which is having an effective computation as an argument, it's actually not, because this really treats it as data in a way. And so the search procedure, the sort of new version, does the same thing as before, except it also emits these hooks. And the transformers are just handlers for these effectful computations. Now there's a slight problem, which is that we want these transformers to be compositional. And so what each transformer sort of does is it handles this effect. It deals with its own piece of state. It makes its own decisions, and then re-emits the effect just with a smaller signature, so that other transformers down the line can look at their piece of state, and so on and so on. And what we do to achieve that is we sort of create this big like tuple list kind of thing of states, like a stack of states, and each transformer in sequence looks at its own part of that state and does its own things. But thankfully, that's all sort of abstracted away, and all a user needs to do to implement one of these things is to just specify the logic of the transformer itself. So this is the actual implementation of depth-bounded search. I'll walk you through sort of everything. You have this make transformer function that takes a description and creates this effect handler. It needs to know the initial piece of state, so it starts with a depth of 0. We don't use eval state, so that's just a unit. And then one thing you need to know is what to do with the evaluation state when you find a solution, which is just nothing because that's a unit. What to do with the tree state when you find a branch, and that's successor in every branch because you're incrementing the depth. And then what to do sort of when you're popping from the queue and you're making decisions about what to do next, which here says that if the depth hasn't exceeded the depth limit, do nothing. Otherwise, trigger a failure and cause backtracking. And sort of we can chain these things as long as we want to modify the behavior of search. Now that's quite a lot of effect handlers in sequence, right? That was 5 handlers right there, one after the other. And these things are not particularly efficient, right? These are just folds over a free monad. And so these are really, really, really slow. So what we did was we staged them. And really, this is just extremely simple, right? The key idea is that given 2 transformers, we can just merge them together with staging to create one single sort of thing. All the user has to do is sort of switch from just functions to these code transformations. And this lets us sort of fuse together these transformers into one big one. And all that's left to do once you have this sort of one big transformer represented as a code transformation is that in the search procedure, wherever you would have emitted an effect, now you just insert this code. And so that's extremely simple. That's like it's sort of a few lines of Haskell. But what this earns us is quite an impressive boost in performance. This is just an example. We're solving 12 queens with these 3 transformers linked after the other. That's depth-bounded search, and then a randomization thing, and then a node bound. And it goes from 30 seconds to under 3. So that's just with this very, very simple transformation of the code from a bunch of handlers into just one handler. And which is surprising because the constraint solver, which is the part that actually does the useful work, is the same. It does the same work, it takes the same amount of time. We're just removing overheads and getting these huge improvements. All right, that was it. Thank you. Good.
Great. Questions?
Thank you for the great talk. How is the performance improvement compared to the MCP approach?
So the MCP approach, that's a good question. Actually, I wanted to do a comparison between that for a long time. I just can't get the old code to compile. But what they did back in MCP usually was they were like generating C++ code from things to like do that. So it's well, that's sort of the sequel to MCP, where they were just sort of gave up on trying to do it functionally, and they just had a functional description of things, but then they generated C++. And so the old MCP code, that would be a really good thing to try. Unfortunately, I just tried over and over, just couldn't get that code to compile on my machine. So sorry about that.
More questions?
Do you have any? I'll just speak. Do you have any kind of idea what speed up you'd get if you had effect handlers built into the language?
Quite high, probably on the order of that, just because the inefficiency here is that we're working with free monads and folds over those free monads, and that's just a lot of overhead. If you what Nicholas talked about in the keynote, he has this paper where they do fusion, which does a sort of similar thing where they collapse things. The difference between that and what we have here is that we have this very like domain-centric way of doing it, where we exploit these properties of search transformers to create just one fold, whereas they do it in a sort of more generic but less aggressive way. But I do think like this depends a lot on what you're using to implement your effect handlers.
I have a question.
Yep.
Yeah, so you gave those impressive speed ups, but is that a constant speed up? Did you look at how it changes with the size?
Weirdly enough, it increases with size, which is unintuitive, but it seems to increase with size.
That's not that weird, is it?
I mean, I worked on one other project.
So it's better than constant time.
It's better than constant time, yeah. So the speed up grows with the size of the problem. Which is, so I worked on a different project for my bachelor's, which also had to do with constraints. And there too, I noticed that whatever optimization I would do, sort of, it would increase the speed up as the problem got bigger. So I think it's just a sort of in the nature of these things to do that.
Okay. Another question I have is, I was a bit perplexed when you said that given this formulation, you don't need to add all the new features, whereas you did with the MCP version. I got a bit lost on why that is.
So in MCP, their approach was to have that in model type. That's sort of I guess the core problem we're trying to fix about MCP with this thing. It had that really big thing that needed to have a constructor for every single thing you might want to do. Whereas here, we can just use these smart constructors with effects to implement things that aren't otherwise sort of directly represented in. So for example, there's no place in that solver effect that says add a constraint, right? It just works. It just gives you access to the monad, and so you can play around with that much more flexibly with these constructors.
Okay, thanks. Okay, yeah. So next up we have Nada talking about Holy.
Yeah, so this is staged execution from Python to SMT, and the goal here is really to do it for synthesis. So let me show you an example of what that means. So we might have a predicate, a SAT predicate. Here it takes a string, so S, and we want to find an S such that the SAT predicate holds. And here we're saying that we count the number of O's and we get 1,000, and we count the number of OOs and we get 0. And so as a human, you can probably find a constraint for such a string. When we ask an SM, so going through the Holy pipeline, when we, the screen changed a bit, but I'm not sure what's going on. I'll put it back. Is it? Try replugging it again, maybe. Well, okay. There's something. I don't know what changed. Something changed on the resolution, but I think it just shows the 3 instead of 1,000, you might get this solution, which works. And then if you ask an LLM to extrapolate from 3 to 1,000, it might come up with an expression like this, among others. And this one actually works for this example, for the original example of the original size. So we're going to play with these ideas today and look at, in particular, try to find solutions to such puzzles automatically. And the goal is really to play with SMT as a backend and thinking of it, how well can it do synthesis in that context, synthesis of values. So the way it works in the more general case is we're given a predicate in Python, and then we try to find a witness to pass to this predicate so that it returns true. And then whatever we do with the solver, this is where Holy lives. Whatever we do, we recheck at the Python level to make sure we haven't made any soundness issues, soundness mistakes, and things like that. And so the general approach is quite simple, especially if you're familiar with multi-stage programming. The idea is that we overload execution by having symbolic variables. So when this Python program executes, the x variable is symbolic, and then that means that this expression x greater than 5 is lifted symbolically. And then as a side effect of running the Python program, we get this SMT constraint generation, and we then are able to use an SMT solver to solve for this, return a solution, recheck at the Python level. So that's how it works. And in terms of the underlying approach, so we really have, for these symbolic variables or these symbolic expressions, we have a dual representation, something concrete that allows us to propagate constants and have as much information as possible, and something abstract that is about the SMT, the underlying SMT expression that we want to generate for this symbolic value, so symbolic int, symbolic string, or whatever type we want. And in our system, mutations and other features only exist at staging time, so we don't need to have the whole Python semantics completely understood. We can just generate code based on the execution of the Python program. And some virtualization happens through AST rewritings. At first, I wanted to do a lot of the things using Python metaprogramming and overloading, but really, in some sense, to lift built-ins, you have to do a little bit of AST rewriting and things like this. For if, this was just a way to do some optimizations with the other things that I'm going to mention later, which include conditional exploration. So here we can kind of simplify a mutation inside a condition with a rewrite to the if then else expression of an SMT solver and things like this. So we can, in an ad hoc fashion, add more or less optimizations just based on what we want to achieve, and sort of like doing it incrementally to get as many of the benchmark as working as possible. So in terms of the conditionals becoming path exploration, if we have some SAT expression like this in Python, what we have here is when we have this expression, eventually when we want to execute the if statement, Python will call this __bool __ function that is possible to overload at the user level. And so we play this trick of doing a path exploration through the overloading, and I'll get back to this. And just for the intuition here, we basically consider all branches and then guard the branch with the conditions, and then emit implications for these things. So in terms of the overloading of bool, so we kind of pick a path, record the constraints. We have the choice which path to pick first, and we might just pick randomly, or we might just pick deterministically, like maybe a best path or something. And then the driver loop reruns with opposite choices until all paths are explored. So it's not that cheap in some sense. We're doing extra executions, but it's a poor man's way to do like staging of branches, and it has been done in other contexts. So my inspiration over this was Phil Zucker's blog post on picking, where he does something like this in Python, but he picks a branch randomly instead of exhaustively. And there's also the built-in staging library in C++ that does something similar for Path Explorer. So even if your language is not extremely powerful with virtualization, you can still play tricks like this. And so another thing we looked at is encoding lists. So we can either use recursive lists as a data type at the SMT level and basically have kind of lifting what this Python code does using SMT functions that are defined in the target. Or we can also do a thing where here we actually know that the length of the list is 5, so we can explode it into variables at the SMT level, and this is quite more tractable for the SMT solvers to deal with these exploded encodings on bounded lists. So when I first started this project, I tried to use solver bindings in Python. I thought it might make things easier and would allow me to do more different things, but it turns out it was quite hard to get it not to segfault, and using an SMTlib target turned out to be more portable, like having more targets, and also led to collaboration with Kartik from the CVC5 team, kind of trying to see how he could run my benchmark in a faster way. And so the research benefit here is that by using the SMTlib target, we are able to do these, to kind of research these solver-facing encodings as artifacts as well. And there is also a benefit that different solvers do different things. So for example, in our data set, we see that 150 or so are uniquely solved by Z3, 40 uniquely by CVC5, and the majority of them by both. And one thing that happens here is that we do have, because mutation is not understood in the back end, and we also have this problem that we don't actually do any sharing. We could, but turns out we don't really need to do too much sharing because the SMT solvers can handle the explosion that happens here for the problems that we looked at. But basically, in a problem like this, you end up with trees that gets exponentially bigger with the range here n because of that setup. And in terms of results, so this was when the talk was proposed, these were our results. Since then, just by iterating, like just trying to do more things and nothing super new conceptually, but just trying to cover more of the space, which is quite large of Python programs that are in this benchmark. We basically went from 27% to 42% overall on this programming puzzles benchmark. And int is well covered. String is pretty well covered. Float is well covered here. And there's a bit of a weakness with lists, and that's because I'm struggling a little bit to have a good encoding for lists that works for synthesis, and I'll come back to this. So really the main issue with not getting higher numbers is that kind of encoding things in an SMT solver kind of forces a functional reading that is not really compatible with synthesis. And some of the errors we include, so these would be, for example, soundness issues where we return SAT and we find a model, but it's actually failing on Python. So some difference in semantics between the Python level and the SMT level, and other cases where it's returning on SAT, which shouldn't be possible for this benchmark because we know there is a solution and things like this. So there is this kind of work to incrementally improve the results. But already we have some coverage. And one thing we tried is complementing whatever the solver can do with heuristics from LLMs. And so the thing that I showed at the beginning was an extrapolation where we give the smaller instance solution found using an SMT, and then the bigger instance is not solved by the SMT, but by the SMT solver, but we ask an LLM to extrapolate. And actually, this used to be quite good with earlier models, but with the 4.5 Claude models, it turns out that it's able to solve more puzzles without the hints than with the hints. So it's kind of tricky at the boundary of these tools to think, what can you give symbolically to an LLM so that it improves its performance? Or what can the LLM do heuristically so that it improves the solver's performance? And I think that's kind of still very open. And LLMs are already quite good at this. So for example, for the list strings puzzles, which are maybe more intuitive than than the int ones. Claude Sonnet 4.5 solves 79% of them. And so that's much better than what we got with the solver out of the box. And then one thing that didn't work very well is to do these constraint refinements. So starting with SMTlib compiled code and thinking, how can LLMs augment it or use it to do something useful? But I haven't been able to get it to do anything useful with the compiled SMTlib. And just, yeah, so this is just the result that without extrapolation, it does much better. And so I don't think I will have time for a demo, but I think I will just skip to just some of the problems that we've achieved. So in terms of the issues, so I think there's really this verification versus synthesis gap when using an SMT solver in the backend to do not verification but synthesis. And really that's kind of like, if we had relational constraints, we would be able to express that that this is kind of the constraint that we want as a whole, instead of like shoehorning something into the functional side and then checking whether it's 1000 or not. So that is not very conducive to going backwards from here. And so I think in the next steps of this, I want to think about a relational SMT backend, thinking about maybe something like Minicarin for relational search, CHR for composable constraints and SMT dispatch, SMT for theory reasoning still, and because to avoid the bottleneck of always going back and forth between the SMT solver and the search, having some sort of multi-granularity dispatch, and also stage pre-computation. So what we've learned from this project is that, I mean, this basic idea of staging from Python to SMT is not completely new, especially in a more verification setting, but it's kind of easy to get started. It's easy to add more cases. It becomes very ad hoc somehow. You have to cover a lot of the Python semantics to get meaningful results. But conceptually, it's kind of the trick works. And then SMT hits a wall with synthesis. So functional encoding is verified but don't invert. And this is where I think relational backends are needed. And LMMs are already strong at guesses. This benchmark that I'm actually maybe over specializing to in the setting wasn't in the context of like neural systems, and LLMs are quite good at it already. And it was a question to see how far I could push the symbolic side of this. And the scaffolding that we had to communicate between the LLM and the SMT quickly became obsolete in some sense between LLM and Holy. And so we can think of smaller witnesses helped older models, but not current ones. And soundness is easy in the system. It's just rechecking things at the Python level. And so it makes it easy not to trust the solver encodings or the LLM guesses. And so that's what I had for today. And I thank the people I discussed this project with and collaborated with. Thank you.
Do we have any questions? Yes.
Thank you for the interesting talk. I have a question about the LLM and the comparison of the performance of LLMs and Holly. So, like, are the results complementary, or the LLMs completely like subsumes the performance?
So I mean I didn't run the whole benchmark on LLMs. I should at some point probably, but I think it was in the case of the list string, for example, there were a few list string problems that Holy got and the LLM didn't got, but much more the other way around. So I think there can be some complementary things, especially with ints when you have arithmetic computation that is advanced. Yeah, so I find that LLMs, I also gave them a lot of leeway because they were allowed to make many guesses, and then I would just pick the ones that work. So it was pretty generous. But I would say I don't have critical data to say whether it's complementary or not. I know that there are some like significant non-overlap. Yeah.
Thank you.
Okay, let's thank the speaker again and move on to the next talk.
batch.
Okay, so sorry about the technical difficulties. We're running a bit behind time, but I think we can just run over. So don't worry about fitting your talk in. So yeah, next up is Cade.
Sure, thank you. So we're here to talk about towards cumulative semantics. So the crux of our research is trying to preserve time. So lost work is lost time. And without reuse, every analysis that you build is kind of like a tool that only has one function. So as a result, it often gets left behind, and you lose the time you spend implementing it. So in this sense, like a screwdriver with one head is kind of like a monolithic interpreter. So every time you write an evaluation, if you have one interpreter for that evaluation that's not generic, you lose all the time as you move on to new functions. So in this sense, we're going to walk through a simple expression language. So we have expressions that are either constant numbers, an addition of two expressions, or an if. And here we have if not zero, because we're just dealing with numbers. So our evaluation expression takes in an e and is pinned to int, so it's non-generic. And then we match against the type of expression we have. So for constants, we just return back a constant. For expressions, we evaluate each side of addition, or it's not updating on there. I'm not sure if there's something going on. So yeah, for addition, we evaluate both expressions. So we can see here that evaluation order is pinned. So we have to evaluate the first one, then we have to evaluate the second one. And then for if, we have to either evaluate the true condition or the false. So false is marked by 0 here, and then any other number will give us true. So what if we could build a library of abstract semantics, which would give us a tool that we could reuse depending on the abstract domain that we're operating in? So in this sense, kind of like a drill head would be a generic evaluation function, and then each of these different bits that we can put in are kind of like abstract domains. So in this sense, we have a generic function that can take different domains, allowing us to focus on building new domains instead of building new evaluations. And the terminology we use for this is substantiated. So we say that you substantiate your evaluation with semantics, being an abstract domain. And this is pretty commonplace. So the way that we see this is usually with type classes or with modules. So now evaluation takes in some generic A and returns it. And instead of having pinned semantics for each operation, we have this interface that we adhere to. However, you can see here that usually the evaluation order is still fixed. So that's the second axis of the problem that we tackle. So firstly, an abstract domain is not an abstract semantics. A domain is simply parameterized by the values it can contain and the operations that produce them, but it has nothing to do with control flow. So here we can see that we need to take our expression to either integers, which would be our concrete domain, the interval domain, or something like the symbolic domain. And these introduce domain values, and we implement this via algebraic effects. And the second axis of our problem is control flow modulation. So an abstract semantics is an abstract domain plus the control flow for that specific semantics. So for instance, in the concrete domain, if we encounter an if statement, we can either go through the true branch or the false branch, but we can't go through both. However, for something like the interval domain, we don't always know if we're in the true branch or the false branch, so we have to be able to evaluate both sides and then join their results. So our goal is to have something like a series of components that can be mixed and matched to substantiate some generic evaluation function. So for instance, if we pair branching control flow with the integer domain semantics, we get a substantiated evaluation function. And for us, this would be the concrete semantics of our little language. However, if we decide to pair non-branching control flow with the interval domain semantics, we get a substantiated abstract evaluation for this little language. So our main contributions are using algebraic effects to implement introduction handlers, elimination handlers, and then combine both of them to get what we call cumulative abstract semantics, because you can accumulate these components without rewriting or revising your evaluation function. So the first step is this domain value parametricity. So here, instead of using type classes, we leverage effects. So for plus, we can see we have some generic domain D, and we know that we get 2 values in this domain and then produce a value in this domain. So a handler for this effect for integers would look like simple addition in your meta language, where we have the plus operator. And for intervals, we can give it new semantics where we take the low and high values, add them, and then get a new interval. And we call these introduction handlers because they simply introduce domain-specific values. So for instance here, instead of passing E1 and E2 to this plus and evaluating both sides, we pass the evaluation to this plus I, or plus introduction handler. However, we can see that the evaluation order is still fixed. We still have eval E1 and then eval E2. So now we bring up elimination handlers, which allow us to separate control flow from the abstract domain. So here we can see that for our if not 0 example, instead of having to evaluate the guard, the true and the false, inside whatever structure we're using to abstract the domain, we have the evaluation on the outside, which means that our effect is able to determine control flow and the order of control flow. So here we have a branching handler for our if elimination effect. We can see that we use these Ks, which are continuations in an effect handler, to evaluate the guard value, and then to use that guard value to match against 0 or false. But this throws away one value. So we get our A out, our generic A. But if we want something that evaluates each branch of the if expression, we can use multiple continuations to evaluate the guard, the true branch, and the false branch. And the last step here missing is we need to decide how to join these values to get into our abstract domain A. So these elimination handlers eliminate syntax and modulate control flow. And the main crux of this is that they move the evaluation from inside the device you use to create semantic domains to the outside. So we don't know anything about the order of evaluation in our generic function. And we can see that we pair this with an introduction handler. So the introduction handler determines how values are produced or joined, whereas the elimination handler determines the order of control flow. So one thing that we have to note is values are sometimes joined inside an analysis. So if we have a simple branching control flow, we know there's no joining. We take either the true value or the false value. However, if we want to do non-branching, we evaluate all branches and then pass it to our introduction handler. And here we can have special operations like join. So for the interval domain, we need to join the result of going through true and false instead of throwing one away. And by doing this, we create these little components that we can accumulate, hence the name cumulative abstract semantics. And just to give a final demo through this, we can see if we hit the if guard and we're in the concrete domain, we go through either the true or the false branch. However, if we need to join the result of both the true and false branch, we can swap out the handler for the if elimination. And we can now go through both the true and false branch and then get a value in our domain. And that's everything. Once we get through there, we have this idea of cumulative abstract semantics, and we're currently experimenting with building a large subset of Python and trying to create different abstract semantics for it.
Yeah. Catching up on time here, so time for questions. Yep.
I have a small question. Thank you for the interesting work. I was trying to compare this work with the abstracting definitional interpreter framework, where you write a definitional monadic interpreter and then like swap in different monads to like to interpret like different abstractions, right? So like, how does this compare to that work?
Gotcha. So when we were starting this, initially we were thinking about using a monadic approach, but the issue with that are some of the same issues we saw in earlier talks. We have to deal with transformers and you have to lift. So the main idea here is that the handlers can kind of be stacked on top of each other, so to speak. So your evaluation function remains generic, and you don't have to know anything about the types or transforms in that function. And then you can swap or surround it with different handlers for different semantics.
Isn't that like kind of the approach done in the abstract and differential interpreter? Because like you have a generic differential interpreter, and then you swap in different monads, as in you swap in different handlers, right?
Yeah.
So like,
I guess the main difference there is that when you're using monads, even when you're swapping them out, you still have this notion of a monad stack that you have to lift through. So with the algebraic effect handlers, you kind of lose that added complexity, and you gain the ability to simply have a handling function. And then by swapping those handling functions, you don't have to worry about the plumbing, so to speak. So it makes it a little bit simpler to compose.
got it. Thank you.
Thank you for very interesting talk. Oh. Okay. Do you know the word tagless final?
Tagless?
Invented by Oleg Serov and others.
Yeah.
Tagless one. So your application will look like tagless, almost exactly the same as tagless, what tagless final offers. Now, of course, well, you did some systematic approach, but can you compare your approach with tagless final?
I looked through that really early on, but I'm not super familiar with it, so I don't think I can compare it very well right now.
We have a program that we can, well, define a lot of different interpretations of the same source program. So.
Gotcha. I think the main difference, or at least because I don't remember it super specifically, the advantage that we got with the effects was having multiple continuations, because then we can kind of swap out the order. So in some of the testing, we made some handlers that ran backwards, and we were able to get all the way up to a backwards symbolic evaluation for a really simple language. I'll have to look at that again, but the main thing for us was just kind of having this component that could go forwards, backwards, or non-branching.
There are certainly close connections between tagless representations and handlers, so it's not surprising that you're seeing that. Question here.
Thanks for a nice talk. Do you think you could get rid of the elimination handlers if you made eval and handleable effect, so you could call it at the appropriate times in your introduction handlers?
So I am not sure about that approach. Right now what we're doing is we have two implementations, one with continuation passing, and then one using algebraic effects. So the main idea here that doesn't shine through perfectly with if is when you have sequencing. The elimination effect is really good because you can swap which way you sequence for forwards and backwards. And with the algebraic effects in languages that have them first class, some of them do stack swapping, so you get really high performance using those continuations. So we haven't looked into that yet, but I think that's similar to the CPS style that we're doing right now.
Okay, thanks.
Is that a question here? Yeah.
Oh, sorry, I'm a bit unfamiliar with this, so apologies if this is a silly question. I was just wondering, in the handler for ifs, in the abstract domain, don't you get like a combinatorial explosion if you call the continuation, like on every branch?
So you can get that in certain languages. So one thing that we faced when we started, we were using Coca, is that when you have multiple continuations with with multiple effect types, so here these are different effect types, you have dynamic algebraic effects, meaning it reaches for the closest handler, they're not lexically scoped. So what can happen is the continuations don't capture everything they should. So in a while loop, state wasn't being registered as changing, so we were getting infinite iteration and non-termination. But one way we got around this is if you have one effect type, the scope of each of the sub-effects is known at runtime. So this was able to handle that and kind of correct that issue for us.
Thanks.
Okay, thanks.
Oh yeah, it is plugged in, but
Okay, so this is the final talk of this session and I guess of the workshop. So, Jungwon.
Yeah. Hello, I'm Jungwon An from Seoul National University. Today I'm going to present retargeting and abstract interpreter for a new language by partial evaluation. I'm working on this work with my advisor Kwang Keun-hee and my colleague Jay Lee. Abstract interpretation, static analysis is a very powerful technique. However, it is limited to a small set of languages. It is because building an analyzer is an expensive task. And our goal is to reduce the cost by reusing what we already have. Specifically, we are trying to build a static analyzer for T using a concrete interpreter for T written in S and an abstract interpreter for S. Here, T stands for target and S stands for source language. Key idea is to use partial evaluation. Consider the situation where we partially evaluate the interpreter for S with respect to an interpreter for T, which is written in S. The result is another interpreter for T, which is written in a language that was used for writing the S interpreter. This can be extended to abstract interpreter. So we can specialize an abstract interpreter for S with respect to a concrete interpreter for T. And the results would be some kind of interpreter for T. So natural question is this a sound abstract interpreter? And the answer is yes. Partially evaluating a sound as abstract interpreter produces a sound T abstract interpreter. The proof directly follows from the correctness of two interpreters and partial evaluation. The equality on the left is just a correctness condition for the concrete interpreter, and the membership sign in the middle is a soundness condition of the abstract interpreter. And the last equal sign is just describes what the resulting program, the result program of the partial evaluation behaves. Now the more interesting question would be, how does the resulting abstract interpreter look like? I'm going to demonstrate it using small languages. Here we use an imperative language with fixed size memory for S, and for T we use very tiny assembly-like language with single register and two instruction, which is addition and multiplication. The first ingredient is a T interpreter, which is written in S. The implementation is straightforward. It just fetches the instruction that is pointed by program counter, and according to the instruction, we update the value of the register, and then we advances the program counter. For example, if we are trying to evaluate the program S3 mode 2 with input 42, we run this interpreter with initial S memory, where the first cell stores the register value and the second cell stores the program counter. After two iterations, we get the final register value in the first cell of the memory. The second ingredient is an abstract interpreter for S. We wrote a standard abstract definitional interpreter where the evaluation of the expression is done by recursion with abstract operators, and the evaluation of statements is done by open recursive function, where the control flow is handled by abstract filters and joins. Now that we have two ingredients, we can do partial evaluation. Since the resulting program is a bit verbose, we only include a small portion of the program. Now I'm going to focus on two aspects of this resulting abstract interpreter. The first point is that the abstract operators that were used in S analysis is being reused in the resulting T analyzer. This means that the abstract domain that were designed for S analysis is directly used in the T analysis. And the second point we can observe is that the structure of the interpreter is reflected in the resulting abstract interpreter. For example, the while loop in the concrete interpreter is reflected as a recursive call at the last line, and the case analysis on instruction is reflected as joins of 3 abstract states, where each abstract state represents each case of instruction. So the next question will be, how general is this approach? This motivates 2 directions in future work. The first one is to apply this approach to more realistic settings. For S language, we plan to add more rich features such as functions, heaps, and algebraic data types, which is commonly used for writing interpreters. And for T language, we are trying to apply to more realistic language that resembles JavaScript or Python. And we are also interested in domain-specific languages. These languages are used widely in practice, but they often lack the static analyzer because building dedicated static analyzer for these languages is too expensive. We hope this approach will be particularly helpful for those cases. And the second direction is to study relations between the precisions of S and T analyzers. For example, in our demo, the concrete interpreter used the second cell of the S memory as the program counter for T programs. Therefore, if we want T analyzer to be flow sensitive, the input S analyzer should be sensitive on second memory cell. This is quite arbitrary, so we are investigating to generalize this relation and find a systematic way to derive the necessary S sensitivities for desired T sensitivities. To conclude, partial evaluation can be used for retargeting abstract interpreters. Thank you for your attention.
Talks are getting shorter and shorter. Thanks for a nice talk. Do we have questions? No questions? I guess I have a question. You were composing 2 different interpreters together. Have you thought about having a whole stack of interpreters?
That will be interesting direction, but partially evaluating a single abstract interpreter is still very difficult. So we are first investigating the case involving only 2 interpreters.
That seems very sensible. Any more questions? Nope. Okay, well, let's thank our speaker again. And I think, Ning, are you going to finish up?
Oh, you have.
much.
Okay. Cool. Thanks everyone for staying with us until the last of the program. I'm Yunisia from the University of Toronto, and I'm one of the co-chairs together with Yukiyoshi Kameyama from the University of Tsukuba. And we have a very short PC Chairs report, I promise. First, some information about PEPM 2026. We held 4 sessions today on types and logics, semantics and applications, and invited keynote by Nicolas Wu, and the last session, which is this session on staging and effect handlers. And the preceding has been published in the ACM Digital Library, and you can find in the preceding the abstract for our invited keynote, as well as the 4 papers for all the 5 long talks we had. Oh, and short papers are available in the program as well. Thanks for the reminder. If you just check the program on the website. And we have some information on submissions and reviews. So this year, the paper deadline was set to be October 24th. And we decided to be slightly later compared to the last few years in order to avoid the week of ICFP and Splash 2025. And the reviewing process was single blind. That means the reviewers knew who the authors were, but the author did not know who the reviewers were. And we made sure all paper got at least 3 reviews, and all reviews had roughly 4 weeks, I think, to finish the review, and 1 last week to participate in the PC discussion. And we sent out the order notification on November 28th. And in terms of submission numbers, we had 15 submissions in total, and in the end, we accepted 4 papers, 5 short papers, and 2 talk proposals. Yukiyoshi made some statistics on the number of submissions over the last 5 years. So you can see across the last 5 years, we have a slightly decreasing number of submissions in total. And we have the same number of submissions compared to last year, but we have accepted 1 more 4 paper and 2 more short papers. Also, I consider this as a good signal that we have been keep publishing good quality papers at the PEPM community. So please keep sending submissions. And here are some more statistics on the submissions across countries. So we have roughly 40% of the submission coming from the States, and roughly another 40% coming from the Europe, across Belgium, Netherlands, France, Denmark, and Sweden. And roughly 20% of submission come from Asia, across Korea, Japan, and China. And we have 1 independent researcher.
Is one of them from, like, Mars or somewhere? I mean, the one that says none.
I think independent.
Independent
the
country.
ex-student one we had. I think the first talk in
they
this
don't
session.
have a country.
And we are deeply grateful for the help from the steering committee and also from the PC members who helped out put together an amazing program for PEPM this year. And special thanks go to Sam and Moon, who stepped in to help chair sessions. Let's give them a round of applause. So that's everything I have, and thank you for all the audience who participate in the program, and we hope to see you at PEPM 2027.